Infrared observations from Spitzer and Herschel show dusty, heated gas outflowing from the galaxy's core, while millimeter-wave studies with ALMA reveal a cold molecular component being swept up in the process. These outflows extend over several thousand light-years, affecting regions far beyond the black hole's immediate neighborhood. Such a system offers a compelling case study in the theory of quasar-mode feedback, a process in which a luminous active galactic nucleus injects enough energy into the galactic environment to effectively regulate or even terminate star formation. The evidence here suggests that the black hole is not just passively accreting matter, but actively shaping the fate of the entire galaxy. This insight reinforces the idea that black holes, despite their minuscule size compared to galaxies, can exert galactic-scale influence and drive evolutionary transitions over cosmological timescales. The implications are profound for models of galaxy formation and for understanding the tight correlation between the mass of a central black hole and the properties of its host galaxy's bulge. IRAS F11119 plus 3257 serves as a cosmic bridge connecting the physics of high-energy black hole accretion to the broader astrophysical ecosystem in which galaxies live and die. The winds observed are among the most powerful ever seen, suggesting that this galaxy is undergoing a dramatic phase of transformation, one that may eventually leave it quiescent, depleted, and red. Yet, in this act of destruction, the black hole may also be planting the seeds for the next chapter of cosmic architecture. The dynamics of IRAS F11119 plus 3257 underscore a deeper cosmic tension between creation and annihilation. Star formation thrives in regions rich in cold gas, where gravity can slowly coax molecular clouds into collapsing cores. Yet here, the black hole's ferocious wind acts as an anti-architect, disrupting this delicate process. It's as though the galaxy is caught in a war between its inner engine and its stellar future, a feedback loop where the central power source both fuels and starves its own domain. What makes this galaxy particularly riveting is the speed and efficiency with which energy is transferred from microscopic scales near the event horizon to macroscopic scales across the galactic disk. This is not a trivial feat. The gravitational radius of the black hole spans only light hours, yet its influence spans tens of thousands of light-years. Somehow, radiation and magnetic turbulence from a swirling plasma disk less than a light day wide are coordinating the movement of gas clouds across an entire galactic structure. This orchestration is a hallmark of quasar feedback, and IRAS F11119 plus 3257 is one of the clearest symphonies ever recorded. On a more technical level, spectroscopic data show absorption features consistent with highly ionized iron, suggesting that the wind originates close to the event horizon, where X-ray photons interact with the dense accretion flow. This inner region is so compact and energetic that traditional models of galactic wind, supernova-driven or stellar in origin, cannot account for the sheer force and collimation observed. Instead, the black hole itself appears to be the conductor, leveraging radiation pressure and magnetic forces to launch matter at relativistic speeds. Moreover, this galaxy offers a rare glimpse into a transitional evolutionary stage. It may be caught in the act of quenching itself, suppressing star formation while the black hole consumes the last remaining reservoirs of gas. In a few hundred million years, IRAS F11119 plus 3257 could resemble the many elliptical, red and dead galaxies we see populating the modern universe, where little to no new star birth occurs. These ancient-looking systems may once have been vibrant spirals or irregulars, transformed through the very mechanisms we now observe in action. But there's also a philosophical elegance to be found here. In observing IRAS F11119 plus 3257, we are not merely studying destruction, we are witnessing cosmic governance. The same processes that tear apart molecular clouds are the ones that prevent galaxies from overgrowing, that set the pace for structure formation, that sculpt the cosmic web with balance and feedback. The black hole's violence is not chaotic, it is regulatory. Without such mechanisms, the universe might collapse under the weight of its own ambition, forming too many stars, too quickly, without restraint. The environment around IRAS F11119 plus 3257 is also a vivid reminder that galaxies are not isolated islands drifting quietly in space. They are dynamic, self-regulating ecosystems where energy must be balanced as carefully as in a living organism. The black hole's outflow is akin to a cardiovascular system in overdrive, flushing material outward in great surges, altering the chemistry and temperature of the galactic medium. Gas that once cooled in the shadows between stars is now ionized, heated, and expelled into the circumgalactic halo, where it may wander for millions of years before possibly raining back down or escaping into intergalactic space entirely. These expelled gases are not inert. They carry with them heavy elements forged in ancient stars and supernovae, seeding the surrounding cosmic environment with the building blocks for planets and life. In this sense, the outflow is paradoxically both destructive and creative, a stellar diaspora that enriches the universe while sterilizing the home it leaves behind. The iron, carbon, oxygen, and silicon embedded in the wind may one day become the soil of new worlds orbiting distant suns, far removed from the turbulent heart of their origin galaxy. The sheer luminosity of IRAS F11119 plus 3257 reveals how deeply embedded the black hole's activity is in its galactic identity. This is an ultraluminous infrared galaxy, glowing intensely in the far infrared due to dust grains warmed by both star formation and the energetic output of the active galactic nucleus. But the spectrum of this light tells a story, one in which the dust is not merely a passive reflector, but a participant in the feedback cycle, absorbing high-energy photons, re-radiating them as heat and becoming a tracer of the winds that sculpt the galaxy's fate. It is also a reminder of how much we rely on the full electromagnetic spectrum to piece together such narratives. X-rays reveal the wind's birthplace near the black hole, infrared traces the dust and gas it disturbs, and millimeter waves map the cold molecular reservoirs it sweeps away. Without this multi-wavelength synergy, IRAS F11119 plus 3257 might appear to be just another dusty, distant galaxy. Instead, it stands as one of the most compelling demonstrations of how intimately tied a galaxy's destiny is to the invisible, compact singularity at its heart. Even at such great distances, this galaxy forces us to confront a question that resonates across all cosmic scales: how can something so small, in terms of spatial extent, dictate the future of something so vast? The answer lies in the coupling of energy across scales, a fundamental principle that threads through everything from the weather patterns of Earth to the evolution of the largest structures in the cosmos. In IRAS F11119 plus 3257, this coupling is turned up to its most dramatic register, offering a rare, unfiltered look at the raw power of cosmic feedback in action. If IRAS F11119 plus 3257 continues on its current trajectory, its transformation will likely be both swift and decisive in cosmic terms. The relentless wind from its central black hole will keep excavating the galaxy's gaseous reserves, pushing them outward into enormous shells and filaments that swell far beyond the stellar disk. Over time, these expelled structures may become ghostly halos, dim, diffuse clouds slowly dissolving into the surrounding intergalactic medium. Star formation will fade in the galaxy's interior, first dwindling to scattered pockets in sheltered regions, then ceasing altogether as the last molecular clouds are torn apart or heated beyond the point of collapse. Eventually, the brilliant quasar phase will burn out. With little fuel left to accrete, the black hole will settle into a quieter state, its once blinding radiance dimming to a faint ember of X-ray and radio emission. The galaxy itself will grow redder as its hot, young stars die and are replaced by long-lived, cooler populations. What remains will resemble the giant elliptical galaxies we see dominating rich galaxy clusters today, massive, quiescent, and shaped by the memory of a violent youth. Yet buried in its core, the black hole will persist, a gravitational monument to an era when it dictated the very terms of the galaxy's survival. But even this apparent finality is only a pause in a longer cosmic rhythm. The gas flung outward by the outflow is not guaranteed to escape forever. Some fraction, slowed by gravitational pull or cooled over eons, could rain back toward the galaxy in a process known as galactic fountain accretion. If this happens on a large enough scale, the quiescent giant could stir to life once again, rekindling both star formation and black hole activity in a cyclical dance that spans billions of years. In this sense, IRAS F11119 plus 3257's fate is not a straight line toward extinction, but a looping path woven into the grander tapestry of cosmic evolution. On a universal stage, this galaxy is a single verse in an ongoing epic, the story of how matter, energy, and gravity interact to sculpt complexity from chaos. The fierce wind from its heart is more than an astrophysical curiosity, it is a mechanism that regulates the universe's growth, ensuring that galaxies do not form stars recklessly, consuming their fuel in short, unsustainable bursts. Without such feedback processes, the cosmos might have looked very different, brighter, denser, and shorter-lived. Instead, galaxies like IRAS F11119 plus 3257 demonstrate that regulation, even when violent, is essential for longevity on cosmic timescales. And so, light from this distant, turbulent system travels for over 2 billion years before it meets our telescopes, carrying not only the image of a galaxy in upheaval but also the imprint of a law that seems to echo from the smallest atoms to the largest galactic structures, that energy, once concentrated, will always find a way to flow outward, reshaping everything it touches. In that flow lies both the destruction of worlds and the promise of their creation. From a purely scientific standpoint, IRAS F11119 plus 3257 has become a benchmark object for testing models of active galactic nucleus (AGN) feedback. The galaxy's extreme properties allow astronomers to directly compare high-resolution simulations with multi-wavelength observations, bridging theory and reality. In cosmological simulations such as Illustris and Eagle, quasar-driven winds are necessary to reproduce the observed population of massive, quiescent galaxies in the modern universe. IRAS F11119 plus 3257 provides rare empirical evidence that such winds do exist with the predicted energy scales and coupling efficiencies. Observations with NuSTAR have revealed the telltale blue shifted absorption lines of highly ionized iron, Fe-XXV, Fe-XXVI, at velocities approaching 0.25 c, indicating an origin extremely close to the accretion disk. Follow-up studies with XM Newton and Suzaku confirmed the persistence and variability of this ultra-fast outflow, UFO, suggesting a direct link to fluctuations in the accretion rate. The measured mass outflow rates are on the order of hundreds of solar masses per year, with kinetic powers exceeding 10 erg superscript 1, enough to impact the galaxy's entire interstellar medium on relatively short timescales. Radio and millimeter wave interferometry using ALMA and the Very Large Array has traced the cold molecular gas phase of the outflow, revealing structures extending thousands of light-years from the nucleus. These molecular winds have velocities in the range of several hundred to over 1,000 kilometers per second, implying that a significant fraction of the galaxy's star-forming material is being displaced or destroyed. Importantly, the energy budget inferred from these molecular flows is consistent with the coupling efficiencies predicted by AGN feedback theory, typically a few % of the black hole's radiative output. Infrared spectroscopy with Spitzer and Herschel has detected broad OH absorption lines, a classic tracer of dusty, molecular winds driven by radiation pressure on dust grains. These lines provide independent confirmation that the outflow is multiphase, containing hot ionized plasma, warm molecular gas, and cooler dusty components. This multiphase structure is critical, as it shows the wind's ability to interact with and accelerate gas across a range of temperatures and densities. From a theoretical perspective, IRAS F11119 plus 3257 supports a two-stage feedback model. An initial ultra-fast outflow launched from the accretion disk shocks the surrounding interstellar medium, transferring momentum and energy to larger scales. This interaction drives a secondary, slower but more massive molecular outflow that can sweep through the galaxy's disk. Numerical simulations indicate that such processes can clear central gas reservoirs within tens of millions of years, consistent with the observed suppression of star formation in the inner regions of IRAS F11119 plus 3257. Moreover, the system's high infrared luminosity classifies it as a ULIRG, ultraluminous infrared galaxy, a category often associated with late-stage mergers. This raises the possibility that the extreme AGN activity is fueled by gas inflows triggered by a recent or ongoing galactic collision. Deep imaging surveys could reveal tidal features or stellar streams that would confirm this merger-driven feeding scenario. Such a connection would align IRAS F11119 plus 3257 with other merger-induced quasars that serve as cosmic laboratories for studying the transition from starburst-dominated to AGN-dominated feedback. If future observations, particularly with JWST and the upcoming Athena X-ray Observatory, can spatially resolve the interaction zones between the ultra-fast wind and the galactic medium, they will provide unprecedented constraints on the microphysics of AGN feedback. This would refine estimates of energy transfer efficiency, cooling rates, and the conditions under which expelled gas can reaccrete, influencing galaxy evolution models for decades to come. Future research into IRAS F11119 plus 3257 will likely focus on three critical areas: the precise mechanics of wind launching, the efficiency of energy transfer to the host galaxy's interstellar medium, and the long-term fate of the expelled gas. One avenue will involve high-resolution X-ray spectroscopy with next-generation observatories such as SRISM and Athena. These instruments will allow astronomers to measure wind velocity structures, ionization states, and density profiles with unprecedented precision. By resolving subtle shifts and broadenings in spectral lines, scientists can distinguish between radiation pressure, magnetohydrodynamic (MHD) processes, and thermal driving as the dominant wind launching mechanism. If magnetic fields prove critical, it would strengthen the case for magnetocentrifugal acceleration models, in which field lines anchored in the rotating accretion disk sling plasma outward at relativistic speeds. On larger scales, mapping the multiphase outflow geometry is a key objective. Observations with JWST's NIRSpec and MIRI instruments could reveal warm molecular hydrogen emission lines, tracing the interface between hot shocked gas and cooler molecular clumps. Combining these with ALMA's cold gas maps will produce a 3D view of how the outflow carves channels through the galaxy's disk. Such data would clarify whether the wind is isotropic or confined to biconical structures, an important factor in determining how much of the galaxy is affected by AGN feedback at any given time. Another major research question concerns the recycling of outflow material. Deep, wide-field imaging in optical and ultraviolet bands could detect faint arcs or filaments of returning gas, potentially confirming the galactic fountain scenario. If a significant fraction of the expelled gas eventually falls back, IRAS F11119 plus 3257 may experience episodic starburst rejuvenations, altering its predicted evolutionary path. Theoretical work will also advance in parallel. High-resolution hydrodynamic simulations, capable of resolving subparsec scales near the black hole while also modeling kiloparsec-scale galaxy dynamics, will test how small-scale wind physics couples to large-scale galactic evolution. These simulations will incorporate realistic cooling curves, dust physics, and cosmic ray feedback, providing more accurate predictions for mass loading rates and star formation suppression timescales. There is also a cosmological context to explore. How common are IRAS F11119 plus 3257-like systems in the early and intermediate age universe? Large surveys such as Euclid and the Vera C. Rubin Observatory's LSST will be able to identify thousands of luminous AGN in merger-rich environments, allowing astronomers to place this galaxy within a statistical framework. Comparing its properties to similar objects across cosmic time will help determine whether such extreme feedback events are a brief, rare phase or a recurrent stage in the life cycle of massive galaxies. In essence, IRAS F11119 plus 3257 is both an observational anchor point and a stepping stone. It anchors our current understanding of AGN feedback in real, measurable phenomena, while simultaneously pointing toward a future where our ability to model galaxy, black hole coevolution is far more complete. Its study sits at the crossroads of high-energy astrophysics, galaxy evolution theory, and cosmology, making it one of the most scientifically fertile objects in the extragalactic sky. Projecting IRAS F11119 plus 3257 forward, the next 10 to 100 million years are likely to be dominated by energy-regulated depletion of its central gas supply. If the ultra-fast X-ray wind maintains velocities of order 0.2, 0.3 c and a kinetic luminosity at the percent level of the bolometric output, the inner kiloparsec will continue to experience overpressured bubbles and shocks that raise gas entropy and shorten molecular cloud lifetimes. In this regime, the momentum flux of the nuclear wind scales as UFO is almost equal to tau ball/c, with tau of order unity for radiation pressure driving. On kiloparsec scales, the observed molecular flow can show an effective momentum boost of a few to tilde operator 10, consistent with an energy-conserving expansion after shock thermalization. That coupling naturally explains why the cold phase can be accelerated to 10 cubed kms superscript 1 without being instantly shredded. Shocked hot gas does the work, while radiative cooling and magnetic draping help preserve molecular clumps long enough to be entrained. As the gas mass in the nucleus drops, the accretion rate onto the black hole will drift downward from near Eddington toward a radiatively inefficient state. If MBH is 10⁻7, 10⁻8 m, the Eddington luminosity is almost equal to 1.3 times 10⁻45, 10⁻46 erg superscript 1, a sustained kinetic power of a few times 10⁻44, 10⁻45 erg superscript 1 is sufficient to unbind or heat much of the central interstellar medium on a tens of mere clock. Star formation suppression will begin centrally and propagate outward along the wind cones. The specific star formation rate could decline by factors of several, first producing a green valley spectral energy distribution before the system reddens as massive stars age off the main sequence. Over 0.1 to 1 gyre, two pathways bifurcate. If the outflow exceeds the escape velocity of the dark matter halo, a substantial fraction of metals and molecular gas will be lost to the circumgalactic medium. The galaxy will settle into a quiescent phase with only residual, spatially patchy star formation in shielded pockets. If instead much of the flow stalls at tens of kiloparsecs, a galactic fountain cycle may close. Cooled, metal-rich gas returns on ballistic trajectories, briefly rejuvenating star formation in annuli or filaments and refueling the nucleus to trigger additional, shorter AGN bursts. In either case, the duty cycle will imprint itself in stacked age, metallicity relations of stellar populations and in broken power law profiles of warm ionized lines that trace past shock fronts. Several measurable diagnostics can test this timeline. Spatially resolved line ratio maps, e.g., O3/H-beta, N2/H-alpha, should outline ionization cones and shock-excited rims. Line widths should broaden where the molecular and ionized phases interact. Multi-transition CO and HCN ladders will constrain the density and temperature of the accelerated cold gas and reveal whether clumps are primarily momentum or energy-driven. Far-infrared OH doublets will continue to serve as a mass flux meter. Variations in equivalent width over years to decades would track changes in the coupling efficiency. Deep X-ray grating spectra can separate multiple absorption components, probing whether the disk wind is steady, clumpy, or magnetically structured. If magnetic launching dominates, we expect correlated changes between ionization parameter and velocity that differ from pure radiation pressure scalings. Precision energetics link these observables. The mass outflow rate out is almost equal to omega r rho v and kinetic power ec equals 1/2 out v superscript 2, with geometry factor omega and characteristic radius are measured from integral field maps, set hard constraints on feedback work done per unit time. Comparing ec till ball yields the instantaneous coupling, integrating ec over time against the bulge binding energy EB tilde operator, 3/5 gene bulge superscript 2/bulge shows whether the flow can plausibly evacuate the inner gas reservoir. If the observed momentum boost remains greater than or equivalent to 5 and the molecular mass loading stays at hundreds of m-year superscript 1, the model predicts central gas columns will fall below the threshold for widespread gravitational collapse, locking and quenching on less than 300 Mir scales. There are crisp, falsifiable predictions. The stellar velocity dispersion sigma should tighten onto the MBH sigma relation as growth of both components stalls. The dust temperature distribution should skew cooler as compact starbursts fade. Radio continuum maps should evolve from compact, wind-confined structures to more diffuse halos as cosmic rays leak out of the wind bubbles. If a late minor merger delivers fresh cold gas, signatures will include misaligned kinematic axes between stars and gas, a two-component CO line profile, and a transient rise in far-IR luminosity, followed by a short AGN mini-burst and a refreshed, but narrower, ionization cone. On billion-year horizons, demographic context matters. Euler to quasar transitions typically yield massive, bulge-dominated remnants. If IRAS F11119 plus 3257 follows suit, its endpoint is a red, high Sirsic index system with low specific SFR, an aging stellar population, and a quietly accreting black hole radiating at much less than 1% lead. Its metals, however, will not be wasted, either retained in a hot halo that glows softly in X-rays or dispersed into the circumgalactic medium where they enhance cooling for future structures. Thus the eruption phase is not an epilogue but the mechanism by which the system rights its long-term equilibrium. Open questions remain sharp. How finely tuned is the launching mechanism to the accretion state? What fraction of mass flux is truly multiphase versus transiently painted, cold by radiative cooling? How much of the momentum boost is geometric versus thermodynamic? And at what threshold column does star formation become irreversibly suppressed? IRAS F11119 plus 3257 is valuable precisely because each of these can, in principle, be answered with coordinated spectroscopy, interferometry, and time domain monitoring, turning a dramatic outflow into a quantitative benchmark for galaxy, black hole coevolution. A comparative approach sharpens the physical picture. When placed alongside archetypal outflow hosts such as Mark 231, PDS 456, and NGC 6240, IRAS F11119 plus 3257 occupies a regime of high bolometric luminosity with a conspicuously efficient coupling to the cold phase. Its OH 119 micrometers absorption can be modeled with large velocity offsets and broad wings indicative of acceleration rather than pure turbulence, while multi-transition CO observations constrain a molecular mass loading rate plausibly in a few times 10 superscript 2, 10 superscript 3 m-year superscript 1 range. The implied momentum flux exceeds Lball/c by several, consistent with an energy-conserving bubble driven by a faster, hotter inner wind. Photoionization and shock models reproduce observed optical line ratios only when shock velocities of a few hundred km/s superscript 1 are included, demonstrating that radiative and mechanical processes operate jointly rather than in isolation. Geometry and orientation remain pivotal sources of uncertainty. The biconical picture inferred from ionization maps can hide substantial azimuthal structure, clumpy walls, porous channels, and off-axis chimneys that vent energy without leaving symmetric signatures. Integral field spectroscopy with sub-kiloparsec resolution should reveal transverse velocity gradients across the cones. A measurable shear would imply lateral mixing layers where Kelvin, Helmholtz instability shred clouds on the cloud crushing time TCC is almost equal to chi superscript 1 superscript 2 RCL/VSH, with chi the density contrast. The persistence of molecular gas despite these hostile conditions suggests magnetic draping and radiative cooling replenish cold skins fast enough to offset ablation, a scenario testable via high JCO and HCN/HCO ratios that track density and excitation in shocked clumps. Time domain behavior offers an additional lever arm. Variability of the ultrafast X-ray absorber over days to weeks constrains the launch radius to tens, hundreds of gravitational radii, while secular changes in far-IR OH equivalent width over years to decades probe the delayed response at kiloparsec scales. A measurable, albeit smeared,
Correlation between increases in wind kinetic power and subsequent enhancements in warm H2 rotational lines, e.g., S1, S5, would quantify the conversion of mechanical energy into thermal emission. Reverberation-style analyses adapted to outflows, cross-correlating X-ray wind properties with mid-IR shock tracers and radio-free continuum, can bound propagation speeds and dissipation efficiencies without relying solely on geometry-dependent mass estimates. Dust physics encodes further constraints on the coupling. Grain survival in greater than or equal to 300 km S1 shocks is marginal unless dense clumped shield refractory cores, yet IR spectral slopes and silicate features imply substantial dust persists within the flow. If grains survive, radiation pressure on dust can supplement momentum transfer, increasing the effective tau-in is almost equal to tau-ball/c and easing the acceleration of cold gas. Conversely, if sputtering dominates, metals return to the gas phase, enhancing cooling and promoting post-shock molecule formation, a feedback-in-feedback loop that stabilizes multiphase structure. Mid-IR fine structure lines such as Na6, O4, and Fe2, combined with PAH suppression patterns, can discriminate between these regimes and quantify the fractional contribution of AGN versus starburst heating to the infrared luminosity. On galactic scales, the fate of the expelled baryons governs long-term evolution. If the wind loads the circumgalactic medium with metal-rich gas at 1010 K, X-ray halos should brighten and develop entropy profiles characteristic of continuous energy injection. Sunyaev-Zeldovich measurements at high resolution could detect a modest thermal imprint. If instead a substantial portion of the flow stalls and cools, narrow, rotating filaments will rein back with misaligned angular momentum, observable as kinematically decoupled components in CO and as warped dust lanes. Either outcome leaves testable imprints on the stellar body, a radial age gradient marking inside-out quenching, a declining specific angular momentum in the inner kiloparsec, and a migration of the system toward red, bulge-dominated loci in color, magnitude space. Bridging observation and theory requires closing the energy ledger. Measuring the solid angle and filling factor of each gas phase reduces the dominant systematic in and ek, mapping pressure balance between hot, warm, and cold components tests whether the flow is momentum or energy-driven at a given radius, and tracking cosmic ray signatures in broadband radio spectra constrains non-thermal pressure support. With these pieces, IRAS F11119 plus 3257 becomes not just an extreme case but a calibration point, a system where the conversion of accretion power into galactic scale work can be quantified with uncertainty small enough to anchor feedback prescriptions in simulations, turning qualitative narratives of quenching into predictive, falsifiable physics. Expanding the comparative framework further, IRAS F11119 plus 3257 serves as an empirical bridge between the most extreme local ULERGs and luminous quasars at higher redshift, where similar feedback processes are theorized to be common but far harder to resolve. Its relative proximity enables multiband spatial resolution that, at Z greater than or equivalent to 2, would require the resolving power of JWST and ALMA at their limits. This proximity allows direct testing of scaling relations, such as the dependence of wind kinetic power on bolometric luminosity or the relation between molecular outflow mass loading and host stellar mass, in a regime that overlaps the quasar main sequence in both Eddington ratio and IR luminosity density. A central open question is whether the outflow in IRAS F11119 plus 3257 is operating near the theoretical maximum efficiency for quasar feedback. In energy-conserving models, the coupling efficiency between the inner UFO and the large-scale molecular flow is predicted to be on the order of 5 to 10%, which aligns remarkably well with current estimates for this galaxy. If this efficiency represents an upper bound set by hydrodynamic instabilities, radiative losses, or geometric leakage, then IRAS F11119 plus 3257 might be a benchmark ceiling for feedback power in gas-rich merger remnants. Alternatively, if higher efficiencies are achievable in more compact or more massive systems, this galaxy could be an intermediate case,
hinting at even more extreme feedback events in the early universe. Magnetohydrodynamic simulations provide another dimension to the interpretation. State-of-the-art 3D MHD runs suggest that disk-launched winds can maintain coherence and high velocity over kiloparsec scales if magnetic tension channels flow along ordered field lines, reducing mixing losses. If applied to IRAS F11119 plus 3257, such models would predict measurable polarization in synchrotron emission from shock-compressed fields and a distinctive Faraday rotation signature in background radio sources seen through the wind cone. Detecting such effects would confirm that magnetic fields play a dynamic role in feedback, rather than serving as a passive tracer. Chemical diagnostics add yet another layer. The metallicity of the outflow, particularly in the cold and warm phases, can reveal whether the material originates predominantly in the circumnuclear region, enriched by recurrent starbursts and stellar winds, or whether it includes swept-up, lower metallicity gas from the outer disk or tidal debris. Millimeter spectroscopy targeting isotopologues, e.g., superscript 1 superscript 3 CO, C superscript 10, and molecules sensitive to dense, shocked gas, e.g., CO, HNCO, could quantify enrichment patterns and shock chemistry. If the inner wind preferentially entrains nuclear gas, the outflow should exhibit supersolar metallicity and elevated refractory element abundances, signatures of repeated enrichment cycles within the galactic core. Future time domain monitoring can also address the AGN duty cycle in a way static imaging cannot. By systematically tracking both the X-ray UFO and far-IR OH absorption over a baseline of decades, astronomers can measure how promptly the large-scale flow reacts to changes in the central engine. A lag of millions of years between the inner and outer wind phases, consistent with propagation speeds and shock crossing times, would confirm that the observed structure is the integrated outcome of multiple AGN bursts. In contrast, a tighter correlation would imply a more continuous, quasi-steady feedback phase, challenging the prevailing view that Eulert feedback is episodic. In the cosmological context, the long-term evolution of IRAS F11119 plus 3257 is a test case for the broader hypothesis that major mergers are the primary triggers of both luminous quasar activity and rapid quenching in massive galaxies. If tidal debris or faint stellar streams can be imaged with deep optical surveys, possible with the Rubin Observatory or with space-based facilities, then its merger history can be reconstructed and linked directly to the current feedback episode. This causal chain, from merger to gas inflow to quasar ignition to galactic scale outflow, would be one of the clearest empirical validations of the merger-driven feedback paradigm in the local universe. The ultrafast X-ray wind, UFO, remains active, still operating at velocities near 0.2–0.3 c, with kinetic power of a few times 1010 erg superscript 1. On kiloparsec scales, the multiphase outflow continues to clear dense molecular gas from the central regions at rates of hundreds of solar masses per year. Star formation in the nucleus is largely suppressed, with the specific star formation rate, SSFR, reduced by more than a factor of 5 compared to pre-outflow conditions. Morphologically, the galaxy still carries some Eulert characteristics, high dust content, compact IR-emitting regions, but ionization cones are now clearly visible in optical emission line maps. The black hole continues to accrete at a high Eddington ratio, sustaining the luminous quasar phase. ALMA and JWST observations during this period would still detect broad OH absorption, strong CO wing components, and warm H2 shock signatures aligned with the outflow geometry. 100 million years from now. If current coupling efficiencies hold 5–10%, the inner few kiloparsecs will be largely devoid of cold gas. The outflow bubble has expanded well into the circumgalactic medium, CGM, with hot, shocked gas at 1010 K filling the halo. The black hole has likely entered a lower luminosity phase, with the Eddington ratio falling below 0.1, reducing UFO velocity and mass loading. Without new cold gas inflow, the galaxy's star formation drops to residual levels in the outskirts, and the spectral energy distribution, SED, shifts toward the green valley of transitional systems. Morphologically, dust lanes and tidal debris, if present, are fading. The stellar population begins to redden as O and B-type stars age out, and the galaxy's optical color, magnitude position moves steadily toward the red sequence. A faint, ionized halo from past feedback episodes becomes visible in deep narrowband imaging, tracing the history of AGN-driven outflows. 1 billion years from now, the galaxy has fully transitioned into a massive, quiescent elliptical or bulge-dominated lenticular. The central black hole accretes only sporadically from stellar mass loss or minor mergers, producing low-luminosity AGN activity detectable mainly in radio and X-rays. The halo retains a hot, metal-rich CGM enriched by the quasar wind, potentially observable in X-ray emission and absorption lines toward background quasars. If the expelled gas never reaccretes, the galaxy remains red and dead, with little chance of rejuvenation unless a significant merger occurs. Alternatively, if the galactic fountain effect has returned a substantial fraction of the wind material, brief rejuvenation events may have punctuated the quiescent phase, producing small bursts of star formation and transient AGN flaring. Such episodes would leave a layered fossil record in stellar ages and metallicities, traceable through deep spectroscopic surveys. From a cosmological perspective, IRAS F11119 plus 3257 becomes an ordinary member of the red sequence population, but its CGM and stellar population retain the chemical and dynamical imprints of its violent youth, an archival memory that precise spectroscopic studies could decode billions of years later. By modeling these stages with coupled hydrodynamic plus stellar evolution simulations tuned to its current observed parameters, astronomers can produce testable predictions for each epoch, predictions that will help identify analogous systems at different stages in other galaxies. IRAS F11119 plus 3257 is an ultraluminous infrared galaxy, ULIRG, hosting a luminous active galactic nucleus, AGN, whose central supermassive black hole drives one of the most powerful multiphase outflows observed in the local universe. X-ray spectroscopy with New Star, XMM Newton, and Suzaku reveals an ultra-fast outflow, UFO, originating within tens to hundreds of gravitational radii of the black hole, with velocities up to 0.25 to 0.3 c and kinetic powers exceeding 10 erg s superscript 1. These inner winds couple efficiently to the galaxy's interstellar medium, driving massive molecular outflows traced by ALMA Colorado observations and Herschel OH 119 micrometers absorption, with mass loading rates of hundreds of m-year superscript 1 and velocities of 500 to 1,200 km s superscript 1. The measured momentum flux exceeds Lball/c by several, consistent with energy-conserving expansion of shocked wind bubbles into the galactic disk. Multi-wavelength data confirm that the outflow is multiphase, hot, warm, and cold gas components coexist, and spatially extended over kiloparsec scales, with biconical geometry and shock signatures detected in optical and infrared emission line diagnostics. Theoretical modeling and high-resolution hydrodynamic simulations indicate that the observed coupling efficiency, 5–10%, is sufficient to quench central star formation on less than or equivalent to 100 Mir timescales. Chemical enrichment patterns and dust survival within the flow point to significant entrainment of circumnuclear gas, suggesting repeated enrichment expulsion cycles. Projected evolutionary scenarios predict three main phases. 1. Over the next tilde operator 10 Mir, continued quasar mode feedback will maintain high-velocity winds and suppress central star formation. 2. Within tilde operator 100 Mir, the inner few kpc will be gas-poor, star formation will shift to the outskirts, and the AGN will decline to sub-Eddington luminosities. 3. On tilde operator 1 gyre timescales, IRAS F11119 plus 3257 will likely settle as a quiescent, bulge-dominated system with a hot, metal-rich circumgalactic medium, unless late gas reaccretion triggers episodic rejuvenation. As a nearby, luminous AGN with clear signatures of efficient quasar mode feedback, IRAS F11119 plus 3257 offers a rare opportunity to empirically calibrate the coupling between accretion disk winds and galaxy-scale outflows. A coordinated observational roadmap, combining XRISM and Athena X-ray spectroscopy, JWST and ALMA molecular mapping, deep optical/IR imaging, and long-term monitoring, can reduce key uncertainties in feedback energetics, geometry, and duty cycle. These measurements will anchor AGN feedback prescriptions in cosmological simulations, improving our understanding of galaxy, black hole coevolution from the local universe to the peak epoch of quasar activity. The interplay between supermassive black holes, SMBHs, and their host galaxies is now recognized as a cornerstone of galaxy formation and evolution theory. Observations reveal tight correlations between SMBH mass and host bulge properties, such as stellar velocity dispersion and bulge mass, suggesting a long-term coevolution mediated by feedback processes. In particular, energetic outflows from active galactic nuclei, AGN, have emerged as a leading mechanism by which SMBHs can regulate star formation and shape the thermodynamic state of the interstellar medium, ISM, and circumgalactic medium, CGM. These outflows, driven by radiation pressure, magnetohydrodynamic (MHD) forces, or thermal winds from the accretion disk, can inject sufficient energy and momentum into their surroundings to quench star formation on galactic scales, redistribute metals, and modify the baryon content of dark matter halos. Among the diverse manifestations of AGN feedback, the so-called quasar mode represents the most luminous and dynamically impactful phase. Quasar mode outflows, often associated with near or super-Eddington accretion rates, are capable of driving multiphase gas from the galactic nucleus at velocities ranging from hundreds to several thousand kilometers per second. Observations across the electromagnetic spectrum, from X-rays tracing hot, highly ionized plasma to millimeter and submillimeter lines probing cold molecular gas, have demonstrated that these outflows can be both massive and multiphase, carrying kinetic powers that represent several percent of the AGN bolometric luminosity. However, direct empirical links between the small-scale physics of disk-launched winds and the large-scale molecular flows that shape galaxy evolution remain rare. IRAS F11119 plus 3257 is a nearby ultraluminous infrared galaxy, ULIRG, that provides one of the clearest examples of such a link. Situated at a luminosity distance of 2.4 GPC, it exhibits both an ultrafast outflow, UFO, detected in X-ray absorption lines of Fe-XXV and Fe-XXVI, and a galaxy-scale molecular outflow traced by broad OH 119 micrometers absorption features and CO emission. The UFO, observed with New Star, XM Newton, and Suzaku, reaches velocities of up to 0.25 to 0.3 c and originates within tens to hundreds of gravitational radii of the SMBH. Its kinetic power, exceeding 10 erg superscript 1, is sufficient, under reasonable coupling efficiencies, to account for the observed molecular outflow mass loading rates of hundreds of solar masses per year. This rare combination of small and large-scale diagnostics in a single object enables direct testing of theoretical predictions that quasar winds can efficiently couple to the ISM via shock-driven, energy-conserving expansion. The galaxy's infrared luminosity, L_IR 10 superscript 1 superscript 2 L_, classifies it as a ULIRG, a population often associated with major, gas-rich mergers. In such systems, tidal torques and gravitational instabilities funnel large amounts of gas into the central kiloparsec, fueling both intense starbursts and rapid SMBH growth. In IRAS F11119 plus 3257, multi-wavelength imaging and spectroscopy suggest that this merger-driven inflow has triggered an AGN powerful enough to expel gas on scales of several kiloparsecs, potentially shutting down future star formation in the bulge. The multi-phase nature of the outflow, hot X-ray gas, warm molecular hydrogen, and cold CO bright clumps, provides a unique laboratory for studying phase transitions, shock physics, dust survival, and magnetic field amplification in AGN-driven winds. Despite these advances, key questions remain. The geometry and covering fraction of the outflow, its duty cycle and variability, and the relative contributions of radiation pressure, MHD forces, and mechanical shocks to gas acceleration are still poorly constrained. The long-term fate of the expelled material, whether it escapes the galaxy or eventually reaccretes via a galactic fountain, is also uncertain, with profound implications for the galaxy's future star formation history. Furthermore, while coupling efficiencies in IRAS F11119 plus 3257 appear to match those required in cosmological simulations to reproduce the observed galaxy population, such empirical determinations are rare, and the system offers a crucial opportunity for calibration. This paper aims to synthesize existing observations of IRAS F11119 plus 3257 across the electromagnetic spectrum, place them within the broader context of AGN feedback theory, and propose a roadmap for future studies that can decisively answer the outstanding questions. By integrating high-energy spectroscopy, millimeter interferometry, optical integral field spectroscopy, and time domain monitoring, we seek to establish IRAS F11119 plus 3257 as a benchmark system for understanding how SMBHs regulate galaxy evolution through quasar mode feedback. The case for powerful, multi-phase feedback in IRAS F11119 plus 3257 rests on a combination of coordinated X-ray, infrared, and millimeter observations, each probing different spatial and physical scales of the outflow. Together, these datasets provide a rare, near-continuous link from the subparsec launching region near the supermassive black hole to the kiloparsec scale structures in the host galaxy's interstellar medium, ISM. High-energy spectroscopy from Suzaku first revealed broad, blue-shifted absorption features in the Fe-XXV and Fe-XXVI lines, indicative of a highly ionized outflow moving at tilde operator 0.25, 0.3 C. Follow-up campaigns with XMM-Newton and NuStar confirmed these detections, improving the velocity constraints and measuring column densities on the order of 10 superscript 2 superscript 3, 10 superscript 2 cm superscript 2. The derived ionization parameters, log psi is almost equal to 4 to 5 erg cms superscript 1, and velocities require a launch radius of tens to hundreds of gravitational radii, placing the origin firmly within the inner accretion disk region. From these data, the kinetic power of the ultra-fast outflow, UFO, is estimated at greater than or equivalent to 10 erg s superscript 1, representing a few percent of the AGN's bolometric luminosity. L_bol is almost equal to few times 10 erg s superscript 1. This coupling efficiency falls within the range required by hydrodynamic simulations to produce realistic galaxy quenching. Temporal variability in the absorption features, observed over timescales of weeks to months, supports a compact, dynamic launching zone sensitive to changes in the accretion rate. Observations with Herschel/Pax targeted the OH 119 micrometers doublet, a well-known tracer of dusty, molecular winds in AGN-hosting galaxies. In IRAS F11119 plus 3257, the OH lines display broad P Cygni profiles with absorption troughs extending to velocities of tilde operator 1000 kms superscript 1. Modeling these profiles yields a mass outflow rate of several hundred m/year superscript 1 in the cold molecular phase. Crucially, the energetics of this large-scale molecular outflow are consistent with being driven by the inner UFO via an energy-conserving mechanism. The momentum flux of the cold gas exceeds L_bol/c by factors of a few, matching theoretical expectations if the UFO shocks the surrounding ISM, thermalizes, and expands as a hot bubble that sweeps up and accelerates molecular clouds. Follow-up mapping with the Atacama Large Millimeter/Submillimeter Array, ALMA, in CO, 1 to 0, and higher J transitions provides a spatially resolved view of the cold gas reservoir. The CO emission reveals high-velocity wings spatially coincident with the galaxy's central kiloparsec, extending along the inferred outflow axis. The observed kinematic asymmetries and line widths are consistent with radial acceleration rather than simple disk rotation or tidal motion. Line ratios from CO, HCN, and HCO further suggest that a significant fraction of the outflowing cold gas resides in dense clumps, potentially shielded from complete dissociation by dust and self-gravity. These dense clumps may represent the long-lived cores of giant molecular clouds surviving in the outflow, implying a multi-phase structure where cold cores are embedded in a hotter, more diffuse medium. Integral field spectroscopy, IFS, with instruments such as VLT/MUSE and Keck/KCWI reveals extended ionized gas emission aligned with the molecular outflow. Line ratio maps using O3/H-beta, N2/H-alpha, and S2/H-alpha show clear evidence for shock excitation at distances of several kiloparsecs from the nucleus. Velocity dispersions in these regions exceed 300 km s⁻1, and profiles are often asymmetric or double-peaked, consistent with biconical outflow geometry. These optical signatures link the large-scale ionized component to the molecular phase and suggest that the interaction between the hot, shocked UFO-driven bubble and the ambient ISM is ongoing and spatially extended. The multi-wavelength evidence for IRAS F11119 plus 3257 points toward a feedback process that begins in the innermost regions of the active galactic nucleus, AGN, and propagates outward through a cascade of physical interactions that couple subparsec winds to the host galaxy's multi-phase interstellar medium, ISM. This section outlines the physical mechanisms involved, the nature of the observed gas phases, and how these results compare to theoretical expectations for quasar mode feedback. The unique combination of small-scale ultrafast outflow measurements and large-scale molecular outflow diagnostics in IRAS F11119 plus 3257 makes it an exceptional target for future campaigns that can close the remaining gaps in our understanding of AGN feedback. High-resolution X-ray spectroscopy with upcoming missions such as RISM and Athena will allow precise resolution of the ionization structure and velocity subcomponents of the wind, constraining its launch radius, mass flux, and possible magnetic field geometry. Multi-phase mapping with JWST's NIRSpec and MIRI, combined with ALMA's high-resolution molecular imaging, will make it possible to construct a complete three-dimensional kinematic model of the warm and cold phases, testing whether the acceleration of the outflow is continuous or occurs in discrete bursts. Time domain monitoring of OH 119 micrometers absorption depth, CO wing flux, and X-ray wind parameters will reveal the duty cycle of feedback, the timescales over which it propagates, and the causal connections between inner and outer flows. Deep optical imaging with the Rubin Observatory or HST could uncover faint tidal structures, clarifying whether a recent major merger triggered the present quasar phase and gas inflow. Parallel advances in 3D hydrodynamic and magnetohydrodynamic simulations, tuned to the observed parameters of IRAS F11119 plus 3257, will generate predictive models for its evolution over the next 10 million, 100 million, and 1 billion years. If the currently observed mass loading rates and kinetic efficiencies persist, IRAS F11119 plus 3257 will likely transition within the next 100 million years from a gas-rich, infrared luminous merger remnant into a quiescent, bulge-dominated galaxy with a depleted central gas reservoir and a hot, metal-rich halo. Should any significant fraction of the expelled gas return through a galactic fountain process, short-lived episodes of star formation and renewed AGN activity could briefly interrupt its quiescence, leaving stratified signatures in stellar ages and chemical abundances. In conclusion, IRAS F11119 plus 3257 stands as one of the most complete and compelling demonstrations of quasar mode feedback in the nearby universe. By providing a direct observational link between the physics of an ultrafast accretion disk wind and the disruption of star-forming gas on galactic scales, it serves both as a validation of theoretical feedback models and as a template for interpreting similar systems at earlier cosmic epochs. Continued, Coordinated multi-wavelength observations will ensure its role as a benchmark for understanding the intertwined evolution of supermassive black holes and their host galaxies, and the way they shape the large-scale structure of the universe over millions to billions of years. Twisting through space like a celestial serpent, PGC 54559 defies the conventional shapes of galaxies. Its body curves with an unsettling elegance, as if a spiral galaxy had been seized and bent mid-motion by an unseen force. From certain angles, it resembles a backbone straining under cosmic pressure, or a worm swimming through the vacuum, coiling with gravitational unease. This galactic contortion hints at a history far more turbulent than a simple rotation around a central bulge. Scientists suspect that such warping is no accident of formation, but the fingerprint of gravitational interactions. Perhaps PGC 54559 once drifted too close to a larger neighbor, whose tidal forces pulled at its arms and core with enough strength to torque its disk. These galactic encounters are not rare, but the specific result, this exaggerated hook, suggests a particularly dramatic event or a series of near collisions that sculpted the galaxy over millions of years. Its curvature isn't just aesthetic, it encodes the story of invisible dynamics, of past proximity, of cosmic negotiations between mass and momentum. What's especially intriguing is how such a distorted shape still holds together. In simulations, galaxies with extreme warps often fragment or settle into a new form. Yet PGC 54559 persists, like a fossilized ripple from an ancient gravitational tide. Its stars continue their orbits, albeit along oddly skewed paths, and its dark matter halo, though invisible, must be playing a crucial role in keeping this strange configuration from flying apart. It's a dance of chaos and order, stretched across kiloparsecs. From a structural standpoint, its morphology challenges our understanding of disk stability and angular momentum conservation. Galaxies are supposed to flatten out over time, their stars settling into a rotational equilibrium. But PGC 54559 resists this narrative. It keeps its twist like a scar, possibly a permanent one. And that opens questions: how resilient are galactic disks to perturbation? Can a shape this irregular still give birth to stars, or is it a relic, post-starburst and fading? Observations in various wavelengths may help decode the mystery. Infrared imaging could reveal whether new stars are still forming in its bent arms, glowing with warm dust and gas agitated by tidal turbulence. Ultraviolet traces might hint at recent stellar births clinging to the edges of distortion, while radio surveys could uncover filaments of hydrogen, either feeding the galaxy or being siphoned away. If the twist disrupted the inflow of gas, PGC 54559 might be on a path toward quiescence, its shape a prelude to dormancy. But if it's still drawing material from its surroundings, then this cosmic worm could be alive and evolving in unexpected ways. Equally fascinating is the possibility of a hidden companion, an unseen dwarf galaxy or dark halo that once brushed past PGC 54559 and left it deformed. Gravitational interactions don't require visible mass to leave an imprint. The warp could be the only visible clue of a long-vanished or now-distant perturber. This makes the galaxy not just an object of study, but a kind of gravitational crime scene, with the curvature as evidence and the stars as silent witnesses. In the broader context of galactic evolution, PGC 54559 is a reminder that not all cosmic structures settle into serenity. Some retain the tension of their past, stretched and torqued into unfamiliar geometries. These anomalies force astronomers to refine their models, to accommodate the strange alongside the orderly. They may also reveal the underlying flexibility of disk galaxies, how much bending they can endure without breaking, how memory is etched into stellar distributions. Like a fossilized ripple in spacetime, PGC 54559 whispers of a dance long over, of forces no longer present but still felt. Its arc is not a flaw, but a signature, of motion, of encounter, of cosmic drama. It remains curled in the dark, not random, not ruined, but uniquely shaped by the invisible choreography of the universe. PGC 54559 is not merely a curiosity, it is a galactic enigma, twisting the expectations of form and function into a shape that refuses easy classification. At first glance, it appears as though a grand design spiral galaxy had been abruptly interrupted mid-formation, its arms grasped and bent into a sinuous hook. The curvature is so extreme that it evokes more organic comparisons than astronomical ones, a cosmic worm gliding through space, or the vertebrae of a celestial spine, arched under some invisible pressure. But behind its strange elegance lies a story of gravitational tension, cosmic memory, and resilience on intergalactic scales. Galaxies are creatures of balance, between rotation and collapse, between internal cohesion and external disruption. For PGC 54559 to exhibit such a pronounced deformation, it must have experienced a powerful encounter, likely a close flyby with a massive galaxy or a tidal interaction that didn't result in a merger, but left a lasting scar. These encounters stretch and shear the stellar disk, pulling stars into new trajectories, redistributing angular momentum and distorting the otherwise flattened geometry. Such interactions are not just moments, they are eras, unfolding over hundreds of millions of years. And the result, in this case, is a shape that breaks symmetry but retains coherence. Computer simulations of galactic interactions reveal that such distortions are fleeting in cosmic terms. Over time, gravity tends to smooth irregularities, re-establishing rotational symmetry unless new forces intervene. The persistence of PGC 54559's warp structure suggests either that the event was relatively recent on astronomical timescales, or that the perturbation was so profound that equilibrium has not yet returned, and may never. Its stars continue to orbit the galactic center, but not in tidy circular paths. Instead, they trace complex, asymmetric routes shaped by the memory of violence. To fully understand PGC 54559, astronomers look beyond optical images. Infrared observations could penetrate obscuring dust, revealing whether molecular gas clouds are being compressed by the deformation, potentially triggering star formation in unexpected regions. A warp might act as a gravitational funnel, channeling material into localized starbursts. Alternatively, the twist may represent a cutoff, where gas inflow has been disrupted, leaving the outer region starved and aging. Radio telescopes could map the neutral hydrogen, exposing telltale streams or filaments extending from the galaxy like trails of escape, evidence of mass loss or exchange. The question of dark matter looms large. Galaxies like PGC 54559 don't just hold themselves together with visible mass. Their ability to resist tidal disintegration implies a massive, stabilizing halo of dark matter, an invisible framework that anchors the stars and gas despite the strain. The shape of the warp could even help map the distribution of this hidden mass, turning the galaxy's deformation into a diagnostic tool. In this sense, its abnormality becomes an asset to science, a window into the gravitational scaffolding of the cosmos. There's also the haunting possibility of a phantom companion, a galaxy that once swept past, exerted its tidal influence, and vanished into the void. Such flybys are difficult to trace unless the culprit leaves other clues, a tail of stars, a bridge of gas, or a shared velocity vector. If PGC 54559 has no visible partner nearby, it may have interacted with something now invisible, either lost in darkness or absorbed in a more distant collision. The curvature of its disk becomes the only surviving evidence of that ghostly encounter, a frozen echo of gravitational dialogue. In a universe of spirals, ellipticals, and lenticulars, PGC 54559 resists tidy taxonomy. It is a reminder that galaxies are not static objects, but evolving participants in a cosmic dance. Each one bears the imprint of its history, and some, like this contorted marvel, wear it on their sleeves. Its form is not a failure of structure but a triumph of endurance, a warped testament to the dynamism of galactic life. PGC 54559 is not simply a cosmic worm. It is a distorted archive of intergalactic interaction, a probe into the limits of disk stability, and a quiet protest against uniformity in the night sky. In studying its twisted beauty, we are reminded that the cosmos does not favor symmetry for its own sake. It favors stories of motion, encounter, resistance, and sometimes, the most fascinating tales are told by the galaxies that refuse to conform. To gaze upon PGC 54559 is to witness the residue of cosmic choreography, where structure and distortion coexist in a delicate, evolving equilibrium. Its bent profile is more than a visual anomaly, it's an astrophysical narrative etched into the fabric of space, a tale written in gravitational language. Each arc and asymmetry carries the weight of billions of years of momentum, collisions, and adaptation. Unlike idealized textbook spirals that seem to swirl in perfect harmony, PGC 54559 whispers of a universe that is not always gentle, yet astonishingly resilient. This resilience is what captivates astronomers. Despite its contorted disk, the galaxy hasn't collapsed into chaos. It hasn't torn itself apart. It hasn't gone dark. Instead, it continues to function, rotating, radiating, possibly forming new stars, and anchoring itself in space with a quiet tenacity. How such a form maintains internal balance is an open question. Theories suggest that in heavily warped galaxies, dark matter halos become even more essential, not just as invisible mass, but as regulators of orbital chaos. Their spherical or ellipsoidal geometry may dampen some of the violent oscillations introduced by tidal interactions, allowing the luminous disk to settle into a new, but deformed, configuration. The warp itself may not be uniform. Some simulations indicate that in such galaxies, different regions can oscillate at different frequencies, a phenomenon akin to galactic precession or nutation, where the disk wobbles subtly over time. This could give rise to resonances, regions of compressed gas or accumulated stars, which might serve as temporary nurseries for star formation. Indeed, astronomers have observed warped galaxies with surprising starburst regions located well outside the central disk, likely ignited by such gravitational compression. Spectroscopy offers another pathway to insight. By examining the Doppler shifts of different parts of the galaxy, scientists can map the kinematic disturbance, the twist in velocity space that mirrors the physical bend. If one side of the galaxy shows stars moving away faster than the other, it may suggest a rolling or folding motion, a three-dimensional deformation not always visible in two-dimensional projections. These kinematic maps could reveal hidden torques, angular momentum exchanges, or the aftershocks of tidal forces that shook the galaxy like a ribbon in wind. Even the color gradients across PGC 54559 may hold secrets. In galaxies, color is a proxy for age. Blue regions suggest younger, hotter stars, while redder tones point to older, cooler populations. If the warp has preferentially stripped gas from one side or funneled it into another, there may be sharp contrasts in stellar population. A sudden shift from youth to senescence along a bent spiral arm would be compelling evidence of directional star formation, or its suppression, driven by gravitational instability. Beyond individual properties, galaxies like PGC 54559 serve as a reminder that the cosmic web is an arena of ongoing interaction. No galaxy exists in a vacuum. Every shape, every structure is a result of countless past relationships, with nearby galaxies, with satellite systems, with flows of gas and dark matter. Warped galaxies act as witnesses to the environmental history of the cosmos. In clusters, tidal effects are amplified, in voids, distortions are rare. Where PGC 54559 resides, and whether it's part of a larger gravitational drama, could contextualize its deformation within the grander stage of cosmic architecture. Philosophically, PGC 54559 invites reflection on the aesthetics of imperfection. In a universe governed by laws of symmetry and conservation, the beauty of a bent galaxy lies in its defiance. It bends, but does not break. It twists, but does not collapse. It is imperfect and therefore alive, still evolving, still participating in the ceaseless transformation of the cosmos. And so, in its arc, we find not just the record of a past encounter, but a question posed to future science: how do galaxies remember what touched them? How long does a cosmic scar last? And what does it mean for structure to endure, even when twisted beyond recognition? PGC 54559 is more than a malformed galaxy, it is a celestial paradox, suspended between beauty and disruption, coherence and chaos. In a cosmos where billions of galaxies trace out elegant spirals, spheroids, or lenticular disks, this warped anomaly asserts itself as a defiant exception, a structural outlier whose very existence forces a re-examination of galactic norms. It invites us to consider a profound question: what happens when a galaxy refuses to settle into symmetry? Its curvature is not merely a surface feature, it is the embodiment of dynamical history. This galaxy has not simply evolved in isolation. Its twisted spine suggests an external event of colossal scale, perhaps a glancing blow from a satellite galaxy, a gravitational harassment in a dense group, or even the gravitational echo of a flyby from a massive, invisible dark halo. These events act not instantaneously, but gradually, reshaping the angular momentum of the disk, deforming its symmetry, pulling its stars along new orbits that form the dramatic hook now etched across light-years of space. Yet this distortion is not a death sentence. PGC 54559 remains structurally intact. Its spiral character is still decipherable. Its stars have not been scattered like debris, and its nucleus remains gravitationally dominant. This defiance of dissolution points to a deep gravitational cohesion, likely supported by an extensive and massive dark matter halo that anchors the entire system against further unraveling. The very warp becomes a living signature of survival. The curvature is a scar, yes, but also a testament to the galaxy's resilience. And within this resilience may lie a deeper mystery. Are galaxies like PGC 54559 evolutionary cul-de-sacs, condemned to drift through the universe in distorted silence? Or do they represent transitional phases, bridges between familiar morphologies? Could the warp eventually settle, unwind, or smoothen into a more typical disk shape over billions of years? Or might new interactions amplify the distortion, pushing the system toward disintegration or a merger? There is no universal answer, because each warped galaxy is a product of unique initial conditions and evolutionary paths. But this uncertainty is part of what makes PGC 54559 so invaluable. Its very irregularity is a clue, perhaps even a missing piece, in the broader puzzle of galactic evolution. From an observational standpoint, warped galaxies like PGC 54559 offer rare laboratories for studying the role of angular momentum redistribution in stellar systems. In a textbook spiral galaxy, the rotation curve, how orbital velocity changes with radius, follows a predictable profile. In warped galaxies, however, this curve can twist, bend, or even bifurcate, depending on the severity and orientation of the warp. Studying these deviations can reveal not only the underlying mass distribution, including dark matter, but also how perturbations propagate through a stellar disk over time. Moreover, the gas dynamics within PGC 54559 are likely anything but simple. In ordinary spirals, gas tends to flow inward along the arms, feeding the central regions and fueling star formation. In a warped system, gas flow can become chaotic or redirected. Shock fronts may emerge where the curvature is greatest, compressing gas clouds and perhaps triggering bursts of star formation in places where none would occur under normal conditions. Alternatively, the warp could inhibit star formation by disrupting gas densities or increasing turbulence beyond the threshold for gravitational collapse. Either way, the curvature becomes not just a geometric oddity, but a direct modulator of galactic metabolism. There's also the matter of magnetic fields. Galactic-scale magnetic structures are difficult to observe, yet they play an essential role in shaping gas flow and cosmic ray propagation. In a warped galaxy, field lines may become twisted, folded, or disrupted, possibly enhancing magnetic turbulence or even generating localized dynamos that amplify field strength. The interplay between gravity, gas, and magnetism in such an environment could lead to emergent behavior not seen in flatter, more orderly systems. And then, there is the metaphysical dimension, a place where astronomy meets philosophy. In PGC 54559, we glimpse the aesthetics of asymmetry, the poetry of gravitational trauma. The galaxy is imperfect, yet enduring. It evokes the idea that damage does not preclude function, that disorder can coexist with stability. Its warped arms stretch like questions across the void. What forces shaped me? What have I survived? What will I become? In a sense, PGC 54559 is not just a galaxy. It is a story, one with characters, stars, conflict, interactions, memory, curvature, and potential, future evolution. It is a relic and a beacon. It embodies the truth that even in a universe governed by strict physical laws, beauty can arise from imbalance, and longevity can follow upheaval. As we observe it across the electromagnetic spectrum, from optical wavelengths to radio waves, from the faint whisper of neutral hydrogen to the searing birth of stars in infrared, PGC 54559 responds not with clarity, but with layered complexity. It tells us that the cosmos is not a static archive of forms, but a living, breathing, evolving expanse of stories still being written. In the curve of PGC 54559, we see ourselves, bent by unseen forces, scarred by past encounters, yet still coherent, still in motion, still illuminated. PGC 54559 is not alone in its distortion. Across the observable universe, astronomers have catalogued dozens, perhaps hundreds, of galaxies with subtle or severe warps, each with their own gravitational fingerprints. Yet few are as visually arresting as this one, whose curvature is so exaggerated, so dramatic, that it seems sculpted by intent. In galaxies like NGC 4013, we see more modest warps, an elegant upward curve in the outer disk, a gentle deviation from symmetry. ESO 510 G13 is another case, more extreme. Its disk appears visibly split, the midplane twisted like a ribbon of light in a slow cosmic wind. These galaxies, too, bear the legacy of tidal interactions. Yet PGC 54559 takes the distortion to a new level, one that challenges not only morphology, but metaphor. When placed alongside these galaxies, PGC 54559 appears less like a deviation and more like an evolution, a different expression of what galaxies can become when left to the will of gravity, motion, and time. The idea that spiral galaxies represent the most orderly structures in the cosmos is itself a kind of illusion. Spirals are inherently dynamic, always subject to imbalance. Warps are the visible tension lines in this balance, the aftermath of a force that arrived, tugged, and moved on. Theoretical models suggest that warps can emerge in several ways, from close interactions with satellite galaxies, from gas accretion with misaligned angular momentum, or from the torques induced by dark matter halos that are not perfectly symmetric. Each mechanism leaves different spectral and structural fingerprints. In PGC 54559, the dramatic curvature hints not at gradual accretion, but at sudden trauma, a flyby that didn't kill, but twisted. It's not just the stars and gas that bear this mark. Even the orbits of globular clusters, spherical groupings of ancient stars that orbit in the galactic halo, may be perturbed, tracing out elliptical or tilted trajectories around the warped disk. Studying their dynamics could act like seismology for galaxies, revealing the internal gravitational vibrations that ripple through the system long after the initial impact. There's also a haunting speculation: what if PGC 54559 once was part of a galactic pair, a binary system of two galaxies dancing in a prolonged gravitational embrace? In such systems, one partner may be cannibalized, absorbed, or flung away, while the other retains a warped memory of the encounter. Perhaps PGC 54559 is the survivor of such a drama, its arc the echo of a former partner, now lost in darkness or distance. From a cosmological standpoint, warped galaxies may also hold keys to understanding the distribution and shape of dark matter halos. In simulations, warps often correlate with triaxial halos, those whose mass distribution is elongated or flattened, rather than spherical. These asymmetries in the invisible scaffolding exert torques on the luminous matter, slowly twisting the disk into curvature. If this is the case for PGC 54559, then its deformation isn't just a record of past collisions, but a probe into the geometry of dark matter itself. And still, the galaxy turns. With each rotation, the stars within PGC 54559 trace the wound into motion, looping along arcs that would seem unnatural anywhere else. And yet, this motion is stable. Predictable. A kind of order has emerged from the distortion. Over hundreds of millions of years, the galaxy has restabilized into its new, bent configuration. Not a return to its original form, but an evolution into something stranger. This echoes one of the most profound truths of astrophysics: galaxies are not fixed, they are fluid memories made of stars. If we were to stand upon a planet orbiting a sun-like star within PGC 54559, we would look to the night sky and see a horizon not of symmetry, but of arc. The stars would stretch across the sky in a bent plane, and perhaps astronomers on that world would ask the same question: what happened to us? Who touched our stars? They, too, would peer into the void for clues, and the curvature above them would be the same gentle echo that reaches our telescopes. PGC 54559 speaks not just to astronomers, but to philosophers and poets of the cosmos. Its shape is a reminder that the universe is not made of perfection. It is made of persistence. The twist in its disk is a lesson in survival. The galaxy is bent, not broken. Alive, not extinguished. And more than anything, it is still writing its story. Because in the end, a warped galaxy is a galaxy that remembers. And in that remembrance lies the most extraordinary truth of all, that gravity, in all its invisible brutality, can also be an artist, sculpting galaxies not just into forms of function, but into symbols of history, of consequence, of grace under pressure. In the curvature of PGC 54559, we glimpse the fingerprints of time not as a smooth continuum, but as a pressure, bending, shaping, deforming. Time in the universe is not passive. It stretches structures, erodes symmetries, and leaves behind fossils in the fabric of space. The warp of this galaxy is a memory held in tension. It is the visible record of something that has passed but never truly left, a gravitational ghost, pressed into the orbits of stars. Entropy governs this story. Not merely as decay, but as complexity rising from initial conditions. In thermodynamics, entropy is the measure of disorder, of possibilities, of how systems evolve from simple to complex, from smooth to structured and then into chaos again. PGC 54559 sits in that strange middle, a galaxy suspended between order and entropy. Its shape is no longer the pristine spiral of a young galaxy, nor is it the chaotic debris field of galactic death. It is a warped memory, ordered enough to endure, chaotic enough to change. In this way, PGC 54559 becomes a metaphor not only for cosmic evolution, but for the human condition. We, too, are shaped by forces we did not choose, impacts that twist us, invisible hands that bend our trajectories. We orbit through time with our own distortions, our own asymmetries, carrying forward the consequences of encounters long past. Our identities are warped histories, just like galaxies, formed by proximity, by pressure, by motion through the dark. A spiral galaxy, in its ideal state, is often compared to a perfect clockwork, arms coiling around a center, stars rotating in harmony. But that is theory. In reality, galaxies are messy, layered, changing. Their arms are never fixed. Their symmetry is always breaking, reforming, dancing in response to invisible tides. And perhaps it is in this breaking that they become most beautiful. PGC 54559 is not ideal. It is not pristine. But it is authentic, honest in its deformation, and in that honesty, profound. Its arms do not reach out evenly. They stretch like questions, spiraling not inward, but forward. Toward something unfinished. Toward a future not yet written. Every loop of the spiral carries stars, gas, dust, memory, and potential. Somewhere in those warped arms, new stars may still be forming. Light is still being born in the bent shadows of cosmic trauma. And yet, there's a deeper stillness in its shape. A solemnity. As though the galaxy itself has accepted its transformation. It is not trying to return to what it was. It has become what it is through process, not accident. This is the secret symmetry of asymmetry, that in the cosmos, there are no mistakes, only outcomes. And in that frame, PGC 54559 is not a broken spiral. It is a new form of order. There is also something sacred in its silence. Unlike supernovae or quasars, this galaxy does not shout. It does not flare violently. It endures. It holds its story not in brightness, but in form. It remembers quietly, and this quiet memory is its message. It tells us that some truths are not explosive, they are curved. Bent. Softened by time. We often look at galaxies as scientific data, mass, velocity, metallicity. But PGC 54559 challenges that reduction. Its very appearance demands interpretation. It is not just what it is, but why it is, and how. This galaxy asks us to look deeper, not just with instruments, but with insight. It invites us to feel the history of the universe not as something cold and distant, but as something that lives in form. In shape. In curvature. In scars. Because galaxies do scar. They do not heal like organisms, but they carry the marks of all they have encountered. These marks do not fade. They become part of the structure. Part of the identity. And in this sense, PGC 54559 is not a distortion. It is a testament. To observe it is to read a line from a book written in gravitational language. A sentence curved across the sky. And as we read it, we see ourselves, not as observers separate from the cosmos, but as part of its same unfolding story, bent, but whole. Twisted, but coherent. Changed, but enduring. PGC 54559 is not a failure of structure. It is the memory of impact. The beauty of imperfection. The architecture of time. What is a galaxy if not a container of memory? Each orbit, each filament of dust, each swirl of hydrogen is a memory in motion, a relic not preserved in stillness, but replayed endlessly in rotation. PGC 54559, with its warped spine, becomes a cosmic brain, its twisted arms the neuronal branches of a universal mind, storing the echo of what once passed through. It has no language, and yet it speaks. It has no thoughts, and yet it remembers. There is something deeply conscious in its form, not in the biological sense, but in the sense that it responded. It was touched, and it did not collapse, it transformed. And that is the essence of awareness, to be affected, to register impact, and to integrate change. PGC 54559 is not static. It is in process, in adaptation, in a continual reconfiguration of form that resembles nothing short of cosmic cognition. It reminds us that memory in the universe is not confined to brains or texts. The universe writes memory into structure, into spiral arms and warped disks, into ionized clouds and magnetic lines, into gravity wells and time loops. Memory is shape. It is imprint. And just as our minds carry the curvatures of our experience in emotional and neurological form, galaxies like PGC 54559 carry theirs in stellar distributions, in curvatures stretched across light years. This raises an exquisite symmetry. As we study the galaxy, it also studies us, silently, passively, by being a mirror. Its curvature reflects our own. The way we spiral through our own lives, pulled and warped by forces we often don't see, relationships, accidents, histories, grief, love, is not so different from the way stars curve under tidal forces. We are all shaped by what comes near. Perhaps that is the most haunting metaphor. PGC 54559 is a portrait of what it means to be changed by proximity. It did not choose its distortion. It did not plan for it. But it carries it with grace. And through that distortion, it has become unforgettable. Unique. It is no longer just another spiral in the dark. It is the spiral that bent. The spiral that survived the bend. And in this survival lies its identity. It teaches us something profound about resilience, not as the refusal to bend, but as the ability to bend without breaking. To incorporate the pull, the pressure, the trauma, and continue turning, shining, holding shape. PGC 54559 is not perfect. It is better, it is true. True to the universe's most sacred pattern, that structure is forged through change. Even its silence is a lesson. It does not cry out like a quasar or explode like a dying star. Its voice is form. Its testimony is curvature. And in that curvature is encoded an entire chapter of the universe, untranslated, but readable. We often seek perfection in symmetry. But the universe, in its deepest truths, is asymmetric. Particles spin unevenly. Time flows in one direction. Matter outweighs antimatter. Life forms from disorder. And galaxies, too, bend, because in bending, they show us how structure persists not in spite of imperfection, but through it. PGC 54559 does not scream. It bends. And in that bending, it reveals the architecture of endurance, an enduring spiral that did not fracture when pulled, that did not collapse when touched by forces vast and unseen. Its curvature is not collapse. It is transformation. And in that transformation, we find a metaphor not just for galaxies, but for time, for memory, for identity itself. Every spiral is a symbol of time. The coil of a snail's shell. The turning of DNA. The hurricane. The whirl of a fingerprint. The spiral of a galaxy. These are not coincidences. They are the geometry of emergence, of life itself. And in PGC 54559, that spiral is bent, as though time itself has curved, not in the relativistic sense, but in the existential one. It is the visible imprint of what happens when history leaves a scar. We imagine galaxies as fixed and far. But they are not statues, they are stories in motion. Their stars orbit not in perfect circles, but in ellipses and loops, like thoughts cycling through the mind. And when something passes close, another galaxy, a wave of dark matter, a rogue current of cosmic gas, those thoughts are interrupted. Paths shift. And a new story begins. The warp is the punctuation in the sentence, the curve in the spiral, the reminder that nothing evolves in isolation. Entropy, the great shaper of everything, does not simply erase. It builds complexity from simplicity. It allows systems to grow more intricate, more beautiful, even as they drift from equilibrium. The warping of PGC 54559 is not a fall from grace, it is an ascension into uniqueness. The pristine symmetry of a spiral may be pleasing, but it is the warped, the twisted, the asymmetrical that carries narrative weight. This galaxy has a past. It is written in curvature. If one were to model its structure in high resolution, tracing the position of every star, every cloud of gas, you would find a dynamical system still in balance, not the balance of stillness, but of rhythm. The stars dance through space not randomly, but in resonance. Even the bend has music. Even the asymmetry has harmony. And beyond its physical reality, the metaphor expands. Because PGC 54559 is not just a thing to be measured. It is an image, one that haunts, that stays with you after you've seen it. It is the feeling of being bent by something vast. Of being changed, but not undone. It is the sensation of still spinning, even after the impact. It is what it means to be alive after catastrophe. Just as we carry our own histories in posture, in scars, in memories that bend our lives into new directions, so too does this galaxy carry its past in its form. Its arms are no longer symmetrical. But they are still open. They still reach. They still curve through space, as if to say, I have been altered, but I endure. From a cosmic vantage point, this is the story of everything. The universe itself is a warped spiral. Born in fire, expanding outward, twisted by gravity, shaped by death and rebirth. Stars live and die. Galaxies merge and separate. Structures collapse and reform. Nothing remains untouched. Everything that persists does so by folding change into form. PGC 54559 is not the exception. It is the expression. And we, brief flashes of consciousness within this galactic epoch, can recognize it. Not just with our instruments, but with our intuition. Because we, too, are spirals. Made of atoms forged in ancient stars. Bent by time. Changed by forces we sometimes do not understand. But still orbiting, still luminous, still becoming. Perhaps this is why PGC 54559 moves us. It shows us that survival is a shape. That history is not something you carry behind you, but something you wear. That scars can become structure. That asymmetry can be sacred. It is not broken. It is storied. Not distorted. Remembering. Not irregular. Alive. And so the spiral continues, not in perfect circles, but in imperfect arcs. Not in silence, but in the quiet hum of gravitational memory. PGC 54559 turns still. And with each turn, it reminds the universe, and us, that to be bent is not to be broken. It is to be written into the greater poetry of time. Shall I continue even further, with a closing passage on universal interconnectedness, or bring this cosmic elegy to a final crescendo? PGC 54559 turns, slowly, imperceptibly, but faithfully. Its arms sweep across the deep sky like brushstrokes in the dark, invisible to the naked eye, yet undeniable in their presence. They do not conform to symmetry, not anymore. And that is precisely why they matter. Because nothing in this universe is untouched. Not stars. Not galaxies. Not people. We are all, in some way, warped. By time. By loss. By encounter. By gravity, both literal and emotional. And like PGC 54559, we continue despite it. Through it. Not as the same, but as something reshaped, more complex, more truthful, more beautiful in our asymmetry. The galaxy does not resist the forces that bend it. It yields. And in yielding, it survives. This is not weakness. This is wisdom. The wisdom of 10 billion years, of matter organizing itself into light, then into spiral bent by time. It is the wisdom of the cosmos, that what bends is not necessarily broken. That what curves may be the most stable of all. There are likely trillions of galaxies in the observable universe. Most are unknown to us. Many look similar, ellipticals, spirals, irregulars. But this one, PGC 54559, is unforgettable. Because it speaks. It tells a story, not in words, but in form. Its message is not encrypted in language, but in physics, in light, in gravitational memory. And if we listen, not just with instruments, but with attention, we hear it. You will be shaped by what moves near you. You will be pulled, stretched, bent. You will not be the same. But you will not be less. You will endure. And you will turn. Still shining. This is the universal law, not written in equations, but in existence itself. Interconnection is inescapable. No galaxy forms alone. No being exists in isolation. What passes near leaves a mark. Some pass gently, leaving only faint ripples. Others come close and change everything, forever. We, too, carry these imprints. We call them memories, relationships, dreams, grief, love. The invisible gravitational fields of our lives. They bend our paths. Reshape our orbits. Sometimes we resist. But sometimes, like PGC 54559, we learn to curve with the force. To spiral anew, in a direction we didn't expect. To embody the encounter. PGC 54559 is a cosmic wound that healed in shape. It did not seal over. It did not erase. It remembered. And that memory became architecture. So what are we, then, if not galaxies ourselves? Clusters of memory. Spirals of thought. Energy flowing in patterns inherited from the past. Distorted, yes, but luminous. Unfinished, but real. And just like galaxies, the more deeply we are warped, the more visible our story becomes. This is what the cosmos teaches, not in speech, but in silence full of stars. That resilience is form. That memory is motion. That every scar can become light. That every spiral, no matter how bent, still turns. So let us honor the curve. Let us see in PGC 54559 not a mistake, but a message. A mirror held up to the soul of the universe itself. Bent. Enduring. Alive. Becoming. Somewhere, hundreds of millions of light years away, a single galaxy curves against the cosmic sea. PGC 54559 does not blaze like a quasar. It does not erupt like a supernova. It simply turns. Quietly. Patiently. As if waiting for someone to notice, not just its presence, but its shape. And we have noticed. We have seen the arc of its arms and read them like script on a forgotten scroll. We have traced its bend, not as an error, but as a sentence. A sentence written by gravity, by time, by encounter. A sentence that says, its arms are not broken. They are remembering. They are the trace of something that passed too close, the evidence of a dialogue between mass and motion, between self and other. It is a monument to proximity, to tension, to resilience. It is the visual echo of a galaxy that allowed itself to be altered, and in doing so, survived. What a stunning philosophy it offers us. That permanence is not required for beauty. That balance does not require symmetry. That endurance is not the absence of pressure, but the ability to carry it in your form. PGC 54559 has become a cathedral of motion. A sanctuary of scars. Its asymmetry is not disorder, it is structure written by memory. It has incorporated every encounter into its own architecture, and in that architecture we see the quiet triumph of continuity. And still, PGC 54,559 turns. Out there, in the silence between galaxies, where time stretches across eons, and memory is written not in words but in curvature, the galaxy continues. It does not return to symmetry. It does not erase what happened. It carries its shape as truth. And in that truth lies everything. In that shape is its voice, its beauty, its quiet declaration. I am not a mistake. I am a trace. I am a survivor of form. And I am still here. Its spiral is warped, but whole. Its stars still orbit, not perfectly, but purposefully. Its light has traveled millions of years to tell us of proximity, of endurance, of cosmic memory, and maybe, of us. Because we, too, are galaxies. Each of us carries a warp, a curve from what came close. Each of us continues to shine, not in spite of that bend, but because of it. No path is untouched. No orbit unshaped. No life without gravity. And yet, we move. As long as we move, we live. As long as we shine, we remember. And as long as we remember, we are part of something greater. PGC 54559 is not just a galaxy. It is a message. A mirror. A monument to the truth. That even in distortion, there is harmony. That even in asymmetry, there can be eternity. And that even the most twisted vessel of light is still light. So ends its story. And so begins ours. In the depths of intergalactic space, hidden from the gaze of optical telescopes, Alcyoneys stretches across an almost unimaginable span of 16 million light-years. This vast structure, invisible to the human eye, reveals itself only when observed in radio wavelengths. Its true form is not a glowing spiral or a brilliant elliptical shape, but a pair of immense plasma jets, launched from the heart of a galaxy by a supermassive black hole. These jets, composed of relativistic particles spiraling through magnetic fields, light up the cosmos in radio waves, carving a colossus across the dark void. Alcyoneys is not just large, it redefines what astronomers believed was possible. Larger than any other known radio galaxy, it challenges current models of how such structures grow and evolve. The central engine, a black hole millions or even billions of times more massive than our Sun, feeds on gas and dust, and in the process, releases energy not just inwards but outwards, launching twin lobes of magnetized plasma. These lobes expand far beyond the visible boundaries of the host galaxy, interacting with the intergalactic medium and stretching through regions where galaxies are sparse and silence prevails. Despite its titanic scale, Alcyoneys resides in a relatively quiet cosmic neighborhood, far from the bustling cores of galaxy clusters. This isolation may be part of the reason it has grown so large. With little external pressure, its jets were able to expand freely for hundreds of millions of years. Its discovery only became possible thanks to advanced low-frequency radio observatories like LOFR, capable of detecting faint and extended radio emissions across vast swaths of the sky. This raised a new question: how many other giants like Alcyoneys remain hidden in plain sight, detectable only through their whispering radio echoes? The plasma streaming from its center carries information not only about the black hole's behavior but also about the environment through which it travels. By studying the structure and curvature of its lobes, astronomers can infer the density and turbulence of the surrounding intergalactic gas. In this way, Alcyoneys becomes both a monument to black hole power and a probe of the large-scale structure of the universe. Its presence suggests that the cosmic web, the filaments of dark matter and gas connecting galaxy clusters, plays a more active role in shaping these behemoths than previously thought. And still, the mechanisms behind such scale remain partially veiled. What allows a galaxy like this to maintain jet activity for so long? Why doesn't it burn out or collapse under its own energy output? These are questions Alcyoneys poses merely by existing. Its lobes, spanning distances that defy human comprehension, remain silent testimonies to the intricate ballet of gravity, magnetism, and cosmic time. Unlike quasars or blazars whose energetic outbursts are transient and often chaotic, Alcyoneys appears to embody endurance. Its jets, though ancient, are not remnants of a violent past, they are ongoing signatures of steady, long-lived activity. This suggests a finely balanced feedback mechanism between the central black hole and its environment, where just enough material is accreted to sustain the jets without overwhelming the host galaxy or exhausting the fuel supply too quickly. It's a cosmic marathon, not a sprint. One of the most remarkable features of Alcyoneys is the symmetry of its structure. Even across such staggering distances, its two radio lobes remain relatively aligned, implying stability in the orientation of the black hole's spin axis over hundreds of millions of years. In a universe filled with collisions, mergers, and disruptions, this level of coherence is rare. It hints at a remarkably tranquil galactic history, or perhaps at a black hole that has somehow resisted the chaos that typically reorients such jets. The environment surrounding Alcyoneys also seems peculiarly conducive to its growth. The intergalactic medium in its vicinity may be unusually low in density, providing little resistance to the expanding jets. This allows the lobes to extend without significant dissipation, making Alcyoneys not only enormous, but also unusually pristine in structure. Such conditions might be rare, making radio giants of this scale exceptional markers of special regions in the cosmic landscape. As technology advances and radio surveys deepen, more structures like Alcyoneys may be uncovered, but for now, it stands alone, the record holder, the ghostly titan. It challenges our understanding of scale and persistence in the universe. It forces us to ask how the quietest corners of space can hide the loudest relics of galactic activity. It invites new models of jet propagation, black hole feeding cycles, and cosmic evolution over billions of years. Alcyoneys teaches us that not all giants roar in light. Some whisper in radio silence, stretching arms of plasma across the void, sketching invisible lines in the dark fabric of the cosmos. These lines, traced by magnetic fields and relativistic particles, tell stories not just of their origin galaxies but of the unseen architecture of the universe itself, the places where matter, energy, and time unfold in vast, slow symphonies beyond human scale. These symphonies, composed by Alcyoneys and its kind, are not merely background noise in the cosmic orchestra, they are the deep bass, the long, slow rhythms that hold the structure of the universe together. While galaxies shimmer and dance in visible light, radio galaxies like Alcyoneys work silently in the dark, shaping and probing the intergalactic medium. Their jets inject energy into the vast void, heating it, stirring it, perhaps even seeding it with magnetic fields that span millions of light-years. In this way, they may influence the formation of future galaxies and the large-scale flow of matter across the cosmic web. At the core of Alcyoneys lies a paradox, an entity that devours matter to unleash energy. The supermassive black hole anchoring this galaxy is the fountainhead of its immense power, yet it remains invisible. It is the ultimate sculptor, chiseling jets from the raw material of space, but hidden behind an event horizon from which no light escapes. What we see are only the consequences of its presence. The twin jets of relativistic particles, the synchrotron radiation glowing in radio wavelengths, the vast lobes that grow like wings in the dark. This interplay of absence and power speaks to one of the great mysteries of the cosmos, how the most destructive forces can become the architects of creation on a cosmic scale. The plasma jets themselves are astonishing in composition and behavior. Twisting through magnetic fields, they exhibit turbulence, knots, and shock waves, signs of internal dynamics that remain poorly understood. Despite traveling at near-light speeds, they retain coherent structures across distances that dwarf entire galaxy clusters. This coherence implies a highly ordered launch mechanism near the black hole, where magnetic fields are tightly wound and focused, possibly through a relativistic accretion disk or a spinning ergosphere. The physics here dances at the edge of what we can currently simulate or even observe. But Alcyoneys doesn't only inform us about black holes and jets, it opens a window into dark matter. Since its radio lobes extend far beyond the visible matter of its host galaxy, they trace the shape and gravitational influence of the dark halo that surrounds it. These lobes, slowly drifting and curving, respond to gravitational gradients invisible to telescopes. They become tracers of the hidden mass that we believe composes most of the universe. Alcyoneys, in this sense, acts like a cosmic brushstroke painting an outline of the invisible architecture that binds galaxies and clusters together. Its scale also forces us to rethink the timeline of cosmic events. The formation of such enormous lobes is not the product of a brief flare-up or a singular event, it requires hundreds of millions, possibly billions, of years. This timescale is staggering. During the lifetime of Alcyoneys' jet activity, entire stellar populations may have risen and died within the host galaxy. Stars formed, went supernova, and seeded space with heavy elements, all while the silent expansion of radio lobes continued, indifferent and uninterrupted. This temporal layering makes Alcyoneys not just a spatial colossus, but a temporal one too, a monument to cosmic patience. And all of this unfolds in what, optically, appears to be a perfectly ordinary galaxy. This apparent contradiction, a visually mundane galaxy concealing one of the largest known structures in the universe, exemplifies the transformative power of multi-wavelength astronomy. Without radio telescopes, Alcyoneys would have remained undetected, invisible against the backdrop of space. But instruments like LOFAR, low-frequency array, revealed its hidden majesty. LOFAR's sensitivity to long wavelength, low-frequency radio signals allowed astronomers to detect the faint, diffuse lobes extending millions of light-years from the host galaxy. This discovery marked not only a triumph in observational technique but also a turning point in how scientists search for similar radio giants across the sky. The study of Alcyoneys has prompted new theoretical investigations into the factors that control the growth of radio galaxies. Previously, it was thought that powerful jets required dense environments, such as the rich cores of galaxy clusters, to amplify and confine their energy. Alcyoneys, however, appears to reside in a relatively sparse region of space, where the ambient pressure is low. This suggests that under certain conditions, isolation may be an advantage. With little resistance from surrounding gas, the jets can travel much farther, unimpeded by environmental turbulence. This insight may require astronomers to revise their models of radio galaxy evolution, accounting not just for energy output, but for environmental permissiveness. Another fascinating area of research concerns the role of magnetic fields. The radio lobes of Alcyoneys emit synchrotron radiation, which arises when high-energy electrons spiral around magnetic field lines at near-light speeds. By analyzing the polarization and spectral properties of this radiation, researchers can reconstruct the structure and strength of these ancient magnetic fields. These fields may have been amplified and shaped over hundreds of millions of years, providing crucial data on how cosmic magnetism evolves on the largest scales. Understanding these magnetic environments can shed light on everything from the behavior of cosmic rays to the dynamics of galaxy formation. Simulations have also begun to play a larger role in decoding Alcyoneys. High-resolution cosmological simulations, incorporating magnetohydrodynamics and relativistic physics, are now being run to replicate the conditions that might produce such a structure. These models attempt to recreate the full life cycle of a radio galaxy, from the ignition of a black hole jet to the slow inflation of radio lobes, and compare them to observations. Early results suggest that long-lived AGN, active galactic nucleus, activity, coupled with a stable spin axis and a relatively undisturbed galactic halo, could explain the observed features. But Alcyoneys remains a boundary case, a challenge to every model that seeks to understand cosmic extremes. Importantly, its discovery raises statistical questions. If such a massive radio galaxy has remained unnoticed until now, how many others might still be hidden? New surveys using next-generation instruments like the Square Kilometre Array, SKA, promise to map the radio sky with unprecedented detail and sensitivity. These telescopes could uncover thousands of faint, extended radio sources, some potentially even larger than Alcyoneys. Each new detection would help refine our understanding of galactic evolution, black hole growth, and the role of radio mode feedback in shaping the cosmos. The scientific value of Alcyoneys is thus far-reaching. It acts as a gravitational anchor point for future research, connecting observations with theory, individual galaxies with the cosmic web, and local environments with the deep past. It allows astronomers to test the limits of what black holes can do, how matter and energy interact in low-density environments, and how long-term processes can sculpt the largest known features in the universe. Alcyoneys also opens an intriguing dialogue between radio astronomy and cosmology. Its radio lobes act as cosmic weather vanes, subtly distorted by the gravitational currents of the large-scale structure of the universe. By examining the morphology, curvature, and asymmetry of these lobes, researchers can extract information about the density gradients and anisotropies in the surrounding dark matter. In this way, Alcyoneys serves not just as an astronomical object, but as a natural detector, a tracer of invisible scaffolding upon which the observable cosmos is built. This property is particularly valuable when studying the filamentary network of the cosmic web, the sprawling structure composed of dark matter, gas, and galaxies that permeates the universe. Alcyoneys, with its enormous span, likely crosses through one or more of these filaments, offering a rare opportunity to probe their composition indirectly. If one radio lobe appears slightly compressed or deflected, it may indicate interaction with a denser patch of intergalactic medium. Conversely, more diffuse regions may allow lobes to expand more freely. By combining these morphological clues with theoretical models and simulations, scientists can map otherwise invisible structures. Another active area of research concerns feedback mechanisms. The jets of Alcyoneys inject not just energy, but also momentum, magnetic fields, and relativistic particles into the intergalactic environment. This process, known as radio mode feedback, can heat surrounding gas, suppress star formation in neighboring galaxies, and prevent the cooling of hot intracluster plasma. Understanding this feedback is essential to galaxy formation theory, as it helps explain why many massive galaxies are quiescent. Their central black holes effectively sterilize their environments. Alcyoneys, as an extreme example of such feedback, offers a natural laboratory to study these effects over enormous timescales and spatial domains. Additionally, the radio lobes themselves may act as cosmic archives. As they expand, they entrap particles and fields from earlier epochs, preserving a record of the galaxy's past behavior. By analyzing the spectral aging of the synchrotron radiation, essentially measuring how the emitted radio waves lose energy over time, astronomers can reconstruct the history of jet activity. Was the black hole continuously active, or did it undergo cycles of quiescence and reactivation? Does the structure reflect steady feeding, or episodic eruptions spaced over eons? These questions are central to understanding the life cycles of AGN and their broader role in cosmic evolution. Moreover, the spatial orientation of Alcyoneys' jets might encode information about primordial spin alignment. In recent years, studies have suggested that the spins of supermassive black holes, and by extension their jets, may exhibit preferential alignments over vast scales, perhaps influenced by the initial conditions of the universe itself. If multiple radio galaxies like Alcyoneys are found with aligned lobes, it could signal a new layer of cosmic coherence, a bridge between galaxy formation and early universe physics. This would open a profound frontier, linking present-day observations with the quantum fluctuations that seeded structure shortly after the Big Bang. Finally, from a technological standpoint, the study of Alcyoneys pushes the limits of data processing and visualization. Its diffuse lobes required sophisticated filtering techniques to distinguish from background noise. Imaging such faint, extended structures demands careful calibration of radio interferometers and the development of novel algorithms to combine signals from hundreds of telescope stations. In many ways, the discovery of Alcyoneys is as much a triumph of data science as it is of astrophysics, showcasing how machine learning and high-performance computing now stand alongside telescopes in the astronomer's toolkit. The implications of Alcyoneys ripple outward not only across space, but also across disciplines. Its existence forces a re-evaluation of what constitutes a galaxy in the modern era. Traditionally, galaxies are defined by their stellar content, their morphology, and their place on the Hubble sequence. Yet Alcyoneys defies this categorization. Its most prominent features lie far outside its stellar core, in regions devoid of stars, gas, or optical structure. In this sense, it invites astronomers to think of galaxies not just as star islands, but as dynamic engines embedded in, and interacting with, the grander cosmic ecosystem. Instruments like LOFR, and soon the SKA, are reshaping this vision, revealing a radio sky filled with tendrils, lobes, halos, and filaments that are invisible in all other wavelengths. These radio components often tell stories of past violence, ancient outbursts, and the long-term influence of supermassive black holes, stories that cannot be read in starlight alone. Alcyoneys stands as a symbol of this transition, a gateway into a deeper, older, more invisible universe. The faintness of its radio lobes also raises questions about energy dissipation mechanisms. Over millions of years, relativistic electrons lose energy via synchrotron radiation and inverse Compton scattering with cosmic microwave background photons. That Alcyoneys remains visible at all suggests either a continuous or episodically refreshed injection of energy from the central engine. This phenomenon touches on the physics of jet stability, particle acceleration, and magnetocentrifugal launching mechanisms, some of the most complex and least understood areas of black hole astrophysics. As more data becomes available, comparative studies between Alcyoneys and other radio galaxies will offer valuable insights. Why did Alcyoneys grow so large, while others with seemingly similar black holes and environments did not? Is there a threshold, in mass, spin, or halo structure, that allows for such scale? Could subtle factors like black hole spin alignment with the galaxy's angular momentum or early cosmic conditions play a determinative role? Each of these questions represents a line of research that may unlock broader truths about the interplay between matter, energy, and spacetime. There is also the philosophical aspect, the humbling realization that such a giant could remain hidden for so long, unnoticed simply because we were not looking in the right way. Alcyoneys reminds us that the universe is vast not just in scale, but in dimension of perception. Every improvement in our instruments, every new wavelength we learn to observe, reveals another layer of reality. The visible universe is only the tip of a far larger structure, and every hidden Alcyoneys is a whisper from the cosmos urging us to listen more closely. Ultimately, Alcyoneys teaches us patience and scale, not just in kilometers or light years, but in time, complexity, and the quiet persistence of cosmic forces. It is a structure that formed slowly, evolved invisibly, and only recently stepped into our field of view, bearing messages from an ancient past. As we uncover more such giants, we will not only better understand galaxies and black holes, but also our own limited vantage, and the endless depths that remain unexplored. In the wake of Alcyoneys' revelation, a new generation of astronomers has begun to recalibrate their expectations. Where once the limits of galactic influence were confined to a few 100,000 light-years, this discovery shattered the conceptual boundary. A structure stretching 16 million light-years, more than 150 times the diameter of the Milky Way, is not just an anomaly, it is an expansion of the very idea of what a galaxy can become when unshackled by dense environments or energetic constraints. Ongoing observations are now focusing on the fine structure within the lobes of Alcyoneys. High-resolution radio maps reveal subtle variations in intensity and spectral index, suggesting a complex internal landscape shaped by turbulence, magnetic reconnection, and shock fronts. These features serve as records of past variability in jet power, environmental resistance, and even instabilities near the black hole itself. Each ripple in the plasma may correspond to a change in accretion rate, a shift in spin axis, or a gravitational interaction long past. In this way, Alcyoneys is not merely a static monument, but a living archive, inscribed with cosmic events in the language of magnetized plasma. The broader cosmological context is equally compelling. Alcyoneys may belong to a class of fossil radio galaxies, structures where the host galaxy has gone quiet, but the lobes persist for eons, slowly fading. If confirmed, this could help refine the timeline of AGN activity and the duty cycle of black holes. It also reinforces the concept of asymmetric aging, where a galaxy's visible and invisible components follow different evolutionary tracks. A seemingly inactive galaxy in the optical band might still be radiating immense energy across radio wavelengths, influencing its surroundings long after the central engine has gone dormant. In terms of methodology, Alcyoneys has inspired new search strategies. Rather than looking for bright, compact radio sources, astronomers are now developing algorithms to detect extremely faint, low-surface brightness structures across wide areas. These techniques rely on subtracting noise patterns, stacking data, and enhancing diffuse emission signatures, computationally intensive, but increasingly effective. These methods are not only yielding candidates for new giants, but also uncovering intermediate-scale relics that fill in the evolutionary gap between ordinary radio galaxies and ultra-extended ones like Alcyoneys. Alcyoneys has also become a touchstone for educational and public science communication. Its immense scale provides an intuitive and awe-inspiring example for illustrating astrophysical concepts, from black hole jets to cosmic magnetism, from relativistic particles to the structure of the universe. When people hear that a galaxy can stretch for 16 million light-years, it challenges their sense of scale, time, and possibility. It invites not just curiosity, but wonder, the same wonder that has driven science since ancient times. In this sense, Alcyoneys is more than data. It is a mirror held up to our cosmic ignorance and our technological potential, a reminder of how much we have yet to see. As we build more sensitive arrays, as we refine our methods, and as we extend our vision into frequencies never before explored, more giants will awaken from the dark. Each will carry its own secrets, but all will share a common trait. They speak of cosmic endurance, the slow but unstoppable unfolding of energy and structure across the deepest reaches of time and space. In the pursuit of uncovering more giants like Alcyoneys, astronomers are not only scanning the sky, they're rewriting the theoretical frameworks that govern jet propagation, black hole fueling, and galactic ecosystems. One key question now being explored is how cosmic filaments and voids might guide or constrain the growth of radio lobes. Since the cosmic web is composed of an intricate network of dark matter and diffuse gas, it can subtly steer or stretch structures like those of Alcyoneys, shaping their evolution in ways previously underestimated. In this context, Alcyoneys is not an isolated oddity, but a participant in the choreography of the universe's large-scale geometry. To test these hypotheses, researchers are correlating radio galaxy orientations with the known topology of the cosmic web derived from galaxy redshift surveys. Early results suggest that in some regions, radio jets do indeed align preferentially along filamentary axes, implying a coupling between black hole spin and cosmic structure. If Alcyoneys aligns with such a filament, it would strengthen the idea that galaxies and their central engines are not randomly oriented, but are instead embedded in a gravitational and magnetic infrastructure far grander than themselves. Meanwhile, deep learning tools are beginning to play an unexpected role in the next phase of exploration. Trained on thousands of radio images, neural networks are becoming adept at identifying ultradiffuse radio lobes, even when they are buried in noise. These models are uncovering a growing population of hidden giants, which, though not as large as Alcyoneys, still defy previous expectations of galactic scale. As these tools evolve, it may become possible to automatically reconstruct the life history of radio galaxies from their morphology alone, a kind of astroforensics powered by artificial intelligence. Alcyoneys also feeds directly into high-energy astrophysics. The jets and lobes it produces are potential sites for ultra-high-energy cosmic ray acceleration, possibly reaching energies beyond those achievable in Earth's most powerful particle accelerators. Understanding how such particles are energized and confined within the lobes could help solve one of the most persistent mysteries in astrophysics, the origin of the highest energy particles observed striking Earth's atmosphere. Alcyoneys, in this sense, becomes a natural accelerator, a laboratory spanning millions of light-years in which exotic physics plays out over incomprehensible durations. Moreover, these immense jets may act as conduits for chemical enrichment, distributing metals and relativistic particles far beyond the boundaries of the host galaxy. Over time, this feedback could influence star formation in neighboring systems, or even in small satellite galaxies caught in the path of the expanding lobes. In this way, Alcyoneys becomes not only a relic of black hole activity, but also a sculptor of the intergalactic environment, a bridge between isolated galactic processes and the shared history of cosmic evolution. As for the host galaxy itself, it is surprisingly unassuming. A standard elliptical, neither particularly luminous nor peculiar in structure, it offers few clues that such a colossal force resides within. This incongruity highlights a critical point: appearances in astronomy can be deeply misleading. The most extraordinary phenomena may lie beneath the surface, detectable only through careful observation in unconventional wavelengths. Alcyoneys reminds us that the universe often hides its most magnificent structures not behind clouds or distance, but behind frequency, in wavelengths we once ignored, and now must learn to embrace. The silence of Alcyoneys' invisible light underscores a profound lesson in modern astronomy: the cosmos is multi-layered, and each wavelength unveils a different truth. For centuries, human eyes, limited to the narrow band of optical light, constructed a partial vision of the universe, missing vast phenomena that whisper rather than shine. Alcyoneys is one such whisper, its radio lobes stretching across the abyss with a quiet that belies their enormity. They are not luminous like stars, nor explosive like supernovae, but they are enduring, persistent, and immensely powerful in their own domain. The question of why Alcyoneys grew so large continues to motivate multidisciplinary studies. One emerging theory suggests a combination of factors: a high-spin supermassive black hole, a long-lasting supply of low angular momentum gas, and a quiet intergalactic environment. Such a trio could allow the central engine to sustain stable, collimated jets for billions of years, unimpeded by disruptions like mergers or turbulence. These conditions are rare, but not impossible, and Alcyoneys may simply be the cosmic equivalent of a tree that found fertile ground and was left alone for eons to grow. Furthermore, the age of its lobes is now under active investigation. Using spectral aging techniques, which rely on the predictable energy loss of electrons due to synchrotron radiation and inverse Compton scattering, astronomers can estimate the time since each region of the lobes was energized. Initial estimates suggest ages on the order of several 100 million years, if not more. This makes Alcyoneys one of the longest-lived jet systems known, surviving not only its own active galactic nucleus phases but also large-scale cosmic evolution, including the drift of galaxy filaments and the expansion of the universe itself. In upcoming years, telescopes like the Square Kilometre Array, SKA, and INVLA, Next Generation Very Large Array, are expected to reveal many more such systems. With vastly improved resolution and sensitivity, they will allow scientists to trace jet lobe interactions with surrounding gas in unprecedented detail. This may help resolve long-standing mysteries about jet stability, entrainment, and energy transfer on cosmological scales. Alcyoneys, then, becomes the benchmark, the giant against which others are measured, the first of a new class of galactic leviathans. It also raises tantalizing cosmological questions. Could such large-scale radio structures affect measurements of the cosmic microwave background, CMB, through subtle anisotropies? Could their relic particles influence the thermal history of the universe's diffuse gas? Could they help explain the so-called missing baryons, the normal matter predicted to exist, but still undetected in large quantities? If Alcyoneys-type structures are more common than we think, they may account for unseen reservoirs of mass and energy shaping cosmic evolution behind the scenes. From a human perspective, Alcyoneys invokes humility. It exists entirely beyond the reach of our senses, its presence betrayed only by the artificial ears we've built to listen to the universe's longer wavelengths. And yet, it was always there, expanding, radiating, evolving, long before our species ever peered into the sky. In this sense, Alcyoneys is not just a discovery. It is a revelation. It tells us that the universe still holds secrets of staggering proportions, awaiting only the patience, curiosity, and ingenuity to uncover them. Alcyoneys also beckons a new era of astrophysical synergy, a fusion of observational radio astronomy, theoretical modeling, cosmic magnetohydrodynamics, and even particle physics. As its colossal lobes ripple through the intergalactic medium, they provide natural laboratories for studying plasma behavior under extreme, long-duration conditions. The lobes consist of collisionless plasma, a regime where particles interact more through electromagnetic forces than direct collisions, akin to conditions found in the early universe, in solar flares, and in particle accelerators. Understanding how this plasma propagates, cools, and interacts with the surrounding medium has implications far beyond galactic astrophysics. It ties into universal plasma behavior across vastly different scales. The interaction between the expanding lobes and the surrounding intergalactic gas also initiates shock fronts, which may compress and heat the medium. These shock waves can be subtle in low-density environments, but over millions of years, they can gently stir otherwise quiescent regions of space. Such shocks may trigger star formation in distant, diffuse gas clouds or suppress it through heating, illustrating again how Alcyoneys, though seemingly remote, may influence galaxy evolution on a wide scale. It becomes not just a passenger in the cosmic web, but an agent of change, invisible, but impactful. There's also growing interest in relic radiation, low-frequency radio emissions from long-dead AGN lobes that persist for eons. Alcyoneys may be a hybrid of a currently active nucleus and relic lobes, or perhaps it is in the late stages of activity, transitioning into dormancy. If so, its spectral signature may encode this transition. Scientists now use broadband radio observations to track such changes, analyzing the curvature of the synchrotron spectrum to determine whether fresh high-energy electrons are still being injected, or if the system is coasting on its last bursts of momentum. Meanwhile, its role in magnetizing the intergalactic medium cannot be overstated. As its lobes swell and dissipate into the surrounding void, they carry with them tangled magnetic fields, potentially enriching the cosmic web with large-scale magnetism. The origin of cosmic magnetic fields is still an open question. Some may be primordial, others generated by galaxies and ejected over time. Alcyoneys, through its gentle but relentless expansion, likely contributes to this magnetic seeding, acting as a cosmic pollinator across millions of light-years. For those studying black hole spin, Alcyoneys offers another clue. Only fast-spinning black holes can sustain highly collimated, powerful jets for extended periods, especially on the order required to generate 16-million light-year structures. This supports the notion that spin energy, rather than just accretion energy, plays a major role in fueling long-lived jets. Such systems may tap into the Blandford-Znajek mechanism, extracting rotational energy from the black hole via magnetic field lines. In this view, Alcyoneys becomes a testament to the efficiency with which nature can extract energy from rotation, like a cosmic dynamo running on spacetime itself. And still, despite all this, Alcyoneys is quiet. No brilliant flare announces its presence. No supernova or gamma-ray burst flashes from its core. It simply exists, vast, ancient, slow, and steady. It is a reminder that not all cosmic drama comes in bursts. Some is written in silence. Some is told in the invisible language of low-frequency radio waves. Some unfolds not over seconds, but over hundreds of millions of years, and still leaves traces we can study today. Alcyoneys, in its silence and scale, subtly redefines the parameters of cosmic narration. In an era dominated by transient phenomena, explosive supernovae, flickering quasars, fast radio bursts. It is the slow epochs like Alcyoneys that remind us the universe is not only a theater of sudden events, but also a vast canvas of processes that unfold in geological, even cosmological time. Its lobes are not mere byproducts of black hole activity, they are time-engraved sculptures of energy, matter, and magnetism, drawn across space by the steady hand of relativity. This realization reframes the role of galaxies as dynamic entities within the cosmic web. Where once galaxies were treated as isolated islands of stars, Alcyoneys shows that galactic influence can extend deep into intergalactic space, modifying conditions in regions far removed from stellar nurseries or dark matter halos. Such influence isn't dramatic, it's osmotic, persistent, a quiet reweaving of the intergalactic medium through the slow exhalation of magnetized plasma. The interplay between kinetic energy and entropy in this context is now a subject of theoretical interest. As Alcyoneys expands, it injects order into surrounding gas through collimated jets, but those jets eventually dissipate, transform, and heat the medium, increasing its entropy. This conversion of directed energy into thermal background parallels processes thought to have occurred during the epoch of reionization and even inflation in the early universe. Thus, Alcyoneys becomes a small-scale analog of universal thermodynamic flow, bridging microcosmic and macrocosmic physics. Another frontier inspired by Alcyoneys is the study of intergalactic voids, the vast regions between filaments where galaxies are sparse or absent. Because the lobes of Alcyoneys may drift through or terminate in such voids, they offer one of the only natural probes of these regions. Their shape, energy profile, and curvature may reveal previously inaccessible information about void density, residual gas pressure, and the properties of dark energy acting on large-scale structure. In this way, Alcyoneys transitions from being an object in the universe to being a measuring instrument of the universe itself. Astrobiologically, Alcyoneys even raises philosophical questions. If complex life depends on the long-term stability of planetary systems and low radiation environments, then galaxies like Alcyoneys, with jets extending millions of light-years, could either sterilize vast regions or create protected zones depending on their orientation and energy output. Could there be planets in orbit around stars in the path of ancient radio jets, slowly bathed for eons in low-level radiation? Might such exposure alter the chemistry of atmospheres, or even the rate of evolution? These remain speculative, but underscore the interdisciplinary reach of objects like Alcyoneys. In many ways, Alcyoneys is a Rosetta Stone for radiocosmology. Its extraordinary size, faintness, symmetry, and persistence challenge assumptions across multiple domains: black hole physics, jet dynamics, intergalactic medium composition, cosmic magnetism, and even the topology of spacetime. It is an object that speaks every dialect of astrophysics at once: plasma physics, thermodynamics, general relativity, high-energy particle theory, and large-scale structure. And its voice, paradoxically, is a whisper. In the final analysis, Alcyoneys is not just a discovery, it is a paradigm shift. It alters what we look for, how we look for it, and what we assume is possible. It is a testament to the quiet giants of the universe, the slow burners, the silent sculptors, the unseen engineers of cosmic architecture. It reminds us that some of the greatest forces in nature are not those that flash, but those that persist. The legacy of Alcyoneys is just beginning to unfold. Future missions and observatories, such as the Square Kilometre Array, SKA, promise not only to detect more giants like Alcyoneys, but also to capture their detailed evolution over cosmological epochs. With such exquisite sensitivity, these next-generation radio telescopes will unveil the subtle internal structures and magnetic topologies within Alcyoneys' immense lobes, revealing the intricate interplay of turbulence, shocks, reconnection, and particle acceleration. Indeed, from a theoretical standpoint, Alcyoneys poses vital questions about the physics of magnetic reconnection and relativistic turbulence occurring at extraordinary spatial scales. Within its lobes, high-energy particles interact with chaotic, dynamically evolving magnetic fields. Understanding these processes better will feed back into plasma physics, informing research not only in astrophysics but also fusion energy and laboratory plasma confinement. Alcyoneys thus becomes a natural astrophysical laboratory, pushing the boundaries of fundamental physics into new realms. Meanwhile, advanced cosmological simulations incorporating magnetohydrodynamics, MHD, and particle-in-cell, PIC, modeling are beginning to replicate the conditions that created Alcyoneys. These computational models allow scientists to run controlled experiments on black hole jets and their evolution over billions of years, something impossible to observe directly. By comparing simulation outcomes with observational data, astronomers hope to pinpoint the precise environmental conditions and physical processes required to form giants of Alcyoneys' caliber. Moreover, Alcyoneys' sheer longevity challenges the current theories of galaxy black hole coevolution. Typically, active galactic nuclei, AGN, cycles, periods when central black holes are actively feeding and producing jets, are considered transient, lasting tens of millions of years. Alcyoneys forces astronomers to reconsider whether certain galaxies can remain quietly active, sustaining low-level accretion and steady jet production far longer than current models anticipate. Could there be subtle, previously unrecognized mechanisms that maintain stable accretion rates at very low levels? If so, Alcyoneys provides a crucial case study for these processes. There are also fascinating considerations about gravitational dynamics. Alcyoneys, spanning such immense distances, inevitably responds to subtle gravitational perturbations from neighboring galaxy clusters, dark matter overdensities, and cosmic filaments. Mapping subtle distortions in Alcyoneys' lobes could thus yield insights into the large-scale gravitational fields permeating intergalactic space. It becomes not only an astrophysical marvel, but also a gravitational probe that reveals details of the universe's hidden mass distribution. As observational data grow richer, astronomers may even uncover smaller galaxies or gas clouds trapped within Alcyoneys' lobes, satellites swept along in the wake of these giant plasma structures. Such intergalactic hitchhikers could provide unprecedented insights into how galaxies and gas structures interact with highly energetic environments. They may also help measure the lobe's precise energy content, density structure, and magnetic field strength through their gravitational interactions and internal dynamics. Finally, Alcyoneys has become an emblem of astronomical storytelling, an inspiring reminder that some of the universe's greatest wonders do not loudly announce themselves. Instead, they wait patiently in the shadows, whispering their presence through subtle signals, gently encouraging humanity to extend the senses far beyond the familiar and the visible. Alcyoneys reminds us that exploration is not merely about brighter telescopes, but about broader vision, curiosity, and the humility to recognize how limited our perceptions have been. As Alcyoneys continues to unfold its secrets, scientists stand poised on the edge of discovery. Each new finding adds a sentence to a cosmic biography spanning millions of years, composed not of dramatic flares, but of quiet persistence. It is this persistence that makes Alcyoneys extraordinary, a gentle titan, quietly sculpting the invisible architecture of the cosmos. In the end, Alcyoneys invites us to shift our gaze from transient spectacles toward the quiet masterpieces of cosmic time. It is a lesson in humility, revealing that our most advanced telescopes have only begun to probe the hidden, silent giants that shape the cosmos. Its discovery signals not an endpoint, but a beginning, the threshold of a new era where radio astronomy, theoretical physics, and computational science unite to unveil structures far beyond human imagination. Alcyoneys is more than just a record-setting galaxy. It is a cosmic paradigm, a reminder that profound wonders often lie hidden, invisible yet influential, patiently awaiting the moment we dare to listen. As we continue to refine our instruments and expand our understanding, Alcyoneys stands as a silent guardian at the edge of discovery, whispering gently that the universe's greatest stories are not always told in brilliant bursts of light, but sometimes quietly and persistently, across the silent echoes of space and time. At the center of a distant galaxy catalogued as IRAS F11119 plus 3257, astronomers have discovered a phenomenon so extreme that it challenges our understanding of how galaxies and black holes coevolve. Located over 2 billion light-years from Earth, this galaxy is not merely a passive host to its central supermassive black hole, it is being violently reshaped by it. Through the combined eyes of NASA's new star, ESA's XM Newton, and JAXA's Suzaku telescopes, scientists observed a tremendous outflow of matter, an ultra-fast wind, being expelled from the vicinity of the black hole at nearly a quarter of the speed of light. This wind is not a gentle breeze but a furious torrent, carrying enough energy to displace vast quantities of gas throughout the galaxy. It tears through the interstellar medium, quenching star formation by stripping away the raw materials that would otherwise collapse into new stellar generations. The data reveal that the wind is rooted in the very innermost region of the black hole's accretion disk, where intense radiation pressure launches particles outward in powerful jets and flows. The X-ray signatures detected matched theoretical predictions of disk winds, providing a rare observational confirmation of models that describe how black holes can influence galactic evolution on a grand scale. IRAS F11119 plus 3257 is thus not just an ordinary galaxy, it is a laboratory of cosmic feedback. What makes this galaxy especially significant is the clear, multi-wavelength trail of causality that links the behavior of the central black hole with the transformation of its host. Infrared observations from Spitzer and Herschel show dusty, heated gas outflowing from the galaxy's core, while millimeter-wave studies with ALMA reveal a cold molecular component being swept up in the process. These outflows extend over several thousand light-years, affecting regions far beyond the black hole's immediate neighborhood. Such a system offers a compelling case study in the theory of quasar-mode feedback, a process in which a luminous active galactic nucleus injects enough energy into the galactic environment to effectively regulate or even terminate star formation. The evidence here suggests that the black hole is not just passively accreting matter, but actively shaping the fate of the entire galaxy. This insight reinforces the idea that black holes, despite their minuscule size compared to galaxies, can exert galactic-scale influence and drive evolutionary transitions over cosmological timescales. The implications are profound for models of galaxy formation and for understanding the tight correlation between the mass of a central black hole and the properties of its host galaxy's bulge. IRAS F11119 plus 3257 serves as a cosmic bridge connecting the physics of high-energy black hole accretion to the broader astrophysical ecosystem in which galaxies live and die. The winds observed are among the most powerful ever seen, suggesting that this galaxy is undergoing a dramatic phase of transformation, one that may eventually leave it quiescent, depleted, and red. Yet, in this act of destruction, the black hole may also be planting the seeds for the next chapter of cosmic architecture. The dynamics of IRAS F11119 plus 3257 underscore a deeper cosmic tension between creation and annihilation. Star formation thrives in regions rich in cold gas, where gravity can slowly coax molecular clouds into collapsing cores. Yet here, the black hole's ferocious wind acts as an anti-architect, disrupting this delicate process. It's as though the galaxy is caught in a war between its inner engine and its stellar future, a feedback loop where the central power source both fuels and starves its own domain. What makes this galaxy particularly riveting is the speed and efficiency with which energy is transferred from microscopic scales near the event horizon to macroscopic scales across the galactic disk. This is not a trivial feat. The gravitational radius of the black hole spans only light hours, yet its influence spans tens of thousands of light-years. Somehow, radiation and magnetic turbulence from a swirling plasma disk less than a light day wide are coordinating the movement of gas clouds across an entire galactic structure. This orchestration is a hallmark of quasar feedback, and IRAS F11119 plus 3257 is one of the clearest symphonies ever recorded. On a more technical level, spectroscopic data show absorption features consistent with highly ionized iron, suggesting that the wind originates close to the event horizon, where X-ray photons interact with the dense accretion flow. This inner region is so compact and energetic that traditional models of galactic wind, supernova-driven or stellar in origin, cannot account for the shear force and collimation observed. Instead, the black hole itself appears to be the conductor, leveraging radiation pressure and magnetic forces to launch matter at relativistic speeds. Moreover, this galaxy offers a rare glimpse into a transitional evolutionary stage. It may be caught in the act of quenching itself, suppressing star formation while the black hole consumes the last remaining reservoirs of gas. In a few hundred million years, IRAS F11119 plus 3257 could resemble the many elliptical, red and dead galaxies we see populating the modern universe, where little to no new star birth occurs. These ancient-looking systems may once have been vibrant spirals or irregulars, transformed through the very mechanisms we now observe in action. But there's also a philosophical elegance to be found here. In observing IRAS F11119 plus 3257, we are not merely studying destruction, we are witnessing cosmic governance. The same processes that tear apart molecular clouds are the ones that prevent galaxies from overgrowing, that set the pace for structure formation, that sculpt the cosmic web with balance and feedback. The black hole's violence is not chaotic, it is regulatory. Without such mechanisms, the universe might collapse under the weight of its own ambition, forming too many stars, too quickly, without restraint. The environment around IRAS F11119 plus 3257 is also a vivid reminder that galaxies are not isolated islands drifting quietly in space, they are dynamic, self-regulating ecosystems where energy must be balanced as carefully as in a living organism. The black hole's outflow is akin to a cardiovascular system in overdrive, flushing material outward in great surges, altering the chemistry and temperature of the galactic medium. Gas that once cooled in the shadows between stars is now ionized, heated, and expelled into the circumgalactic halo, where it may wander for millions of years before possibly raining back down or escaping into intergalactic space entirely. These expelled gases are not inert. They carry with them heavy elements forged in ancient stars and supernovae, seeding the surrounding cosmic environment with the building blocks for planets and life. In this sense, the outflow is paradoxically both destructive and creative, a stellar diaspora that enriches the universe while sterilizing the home it leaves behind. The iron, carbon, oxygen, and silicon embedded in the wind may one day become the soil of new worlds orbiting distant suns, far removed from the turbulent heart of their origin galaxy. The sheer luminosity of IRAS F11119 plus 3257 reveals how deeply embedded the black hole's activity is in its galactic identity. This is an ultraluminous infrared galaxy, glowing intensely in the far infrared due to dust grains warmed by both star formation and the energetic output of the active galactic nucleus. But the spectrum of this light tells a story, one in which the dust is not merely a passive reflector, but a participant in the feedback cycle, absorbing high-energy photons, re-irradiating them as heat and becoming a tracer of the winds that sculpt the galaxy's fate. It is also a reminder of how much we rely on the full electromagnetic spectrum to piece together such narratives. X-rays reveal the wind's birthplace near the black hole, infrared traces the dust and gas it disturbs, and millimeter waves map the cold molecular reservoirs it sweeps away. Without this multi-wavelength synergy, IRAS F11119 plus 3257 might appear to be just another dusty, distant galaxy. Instead, it stands as one of the most compelling